Hello there, and welcome to Physics with William, where curiosity gets comfortable and the universe is allowed to unfold at an unhurried pace. Tonight, we are stepping toward a question that sounds almost playful at first, the sort of thing you might wonder about while staring at the ceiling long after you meant to be asleep. How many neutrons can you stack before reality breaks? It has a slightly mischievous feel to it, as though we are planning to build a tower out of the most stubborn little objects in nature, and then stand back to see when the cosmos finally clears its throat and says, absolutely not. And yet behind that question sits one of the deepest balances in all of physics, a balance so narrow and so important that much of the visible universe depends on it behaving just so. Before we wander too far into collapsing stars and impossible densities, I would love to know where in the world you're listening from tonight, and what sort of hour has found you there. Perhaps it is late and quiet. Perhaps there is rain tapping faintly at the window, or the low hum of some appliance doing its best impression of background philosophy. Perhaps it is still early where you are and you're only borrowing a little calm before the day properly begins. Either way, it feels strangely fitting to ask such a grounded little question before discussing matter under conditions so extreme that ground itself stops being a very useful concept. If you find this gentle excursion soothing or intriguing or simply a pleasant place to rest your thoughts for a while, I would be very grateful if you gave the video a like and maybe subscribed. It helps this quiet corner of science find other people who might enjoy drifting off while thinking about neutrons, gravitational collapse, and the surprisingly fragile arrangement that allows planets and people to exist at all. I do hope, of course, that the subject is restful rather than alarming. Though if tonight you happen to fall asleep wondering whether the universe is held together by a very narrow compromise between pressure and disaster, well, there are worse lullabies to have. So let us begin slowly, because this is one of those questions that becomes larger the more gently you handle it. If I hand you a pile of bricks and ask how many you can stack before the tower falls, you already understand the basic game. There is weight pushing down, there is structure resisting it, and there is some limit beyond which the arrangement can no longer support itself. Replace the bricks with neutrons and things become much stranger very quickly. Neutrons are not little hard marbles in the ordinary sense. They are particles, quantum objects, residents of a world where matter does not simply sit there like pebbles in a jar. They obey rules that are foreign to everyday intuition, and they can resist being compressed not because they are rigid in the way steel is rigid, but because quantum mechanics forbids certain forms of crowding. That is already unusual enough. Then gravity enters the scene and insists on packing them tighter. Then nuclear physics has its say. Then relativity arrives with the sort of expression that suggests the evening is about to become more serious. What makes the whole thing so fascinating is that the answer is not simply more and more and more until eventually something unpleasant happens. The answer has stages. Very small collections of neutrons are not happy arrangements. They do not simply form neat, durable lumps just because one wishes them to. Build too little, and the thing does not really count as neutron matter in the grand, stable sense we are imagining. There is no tidy, tiny neutron world sitting on your desk. No neutron pebble, no neutron teacup, no neutron paperweight. Nature is surprisingly reluctant to let neutrons gather into ordinary long-lived objects on modest scales. They need extraordinary circumstances and enormous pressure before they settle into the kind of densely packed matter we associate with neutron stars. Then, if you do gather enough matter, and if gravity is strong enough to force the issue, there emerges one of the most dramatic objects in the cosmos. A neutron star, not a metaphorical star, not a poetic description. A genuine astronomical object made when the core of a massive star collapses so violently that ordinary atomic structure is crushed out of existence. Electrons and protons are driven together. Space becomes crowded in a way that almost defies language. Matter reorganizes itself under pressure so intense that a city-sized object can contain more mass than the Sun. This is not merely a heap of neutrons, it is gravity and quantum mechanics locked in a tense arrangement, each refusing to yield completely, and then there is another limit. because even a neutron star is not the final word. Add too much mass, and the same gravity that helped create neutron matter eventually overwhelms the pressure-resisting collapse. The balance fails. The object cannot remain a neutron star. There is no stronger stable arrangement available to hold it up, at least none that can save it in the usual story. At that point, the collapse continues. Space and time themselves become part of the problem, and what was once a neutron star becomes a black hole. So hidden inside our deceptively simple question is a sequence of no, then yes, then no again. Too small, and the structure does not work. Large enough, and you get one of the densest stable objects in the universe. Too large, and stability disappears once more. It is not just a matter of piling up more neutrons like sacks of flour in a warehouse. It is a narrow corridor between different kinds of failure. One side, matter cannot organize itself that way. The other side, gravity wins completely. There is something almost architectural about it, though the building materials are exotic and the contractor is a collapsing star. Reality, it turns out, permits only a very specific range in which neutron matter can exist in a long-lived form. That narrow range matters more than one might expect. It is part of why some stars explode as supernovae rather than quietly fading away. It is tied to how the heaviest elements are forged and scattered into space. It affects whether the aftermath of a stellar death becomes a neutron star or a black hole. And through those outcomes, it reaches all the way to planets, oceans, chemistry, and eventually to creatures who lie awake asking unreasonable questions about neutrons. That, perhaps, is the first thing worth appreciating. This is not an obscure curiosity detached from ordinary life. It sounds obscure, certainly. If you mention neutron stacking at a dinner party, some people will quietly edge toward the snacks. But the stakes are enormous. The universe is not merely filled with stars shining serenely in the dark. It is also a place where stars die, cores collapse, matter is squeezed, and the rules governing that squeezing determine what kinds of remnants are left behind and what materials are returned to space. The calcium in your bones, the iron in your blood, the gold in jewellery, the iodine in your body, all these owe their existence to stellar processes that depend on what matter can and cannot withstand under colossal pressure. Still, before we get carried away and leap straight into exploding stars, it helps to slow down and ask a simpler question. What exactly is a neutron, and why should stacking them be difficult in the first place? After all, we hear about neutrons early in school, usually introduced as one of the familiar residents of the atom, living in the nucleus beside protons with a sort of quiet middle child energy. They carry no electric charge. They help bind nuclei together. They sound steady and useful and not especially dramatic. But a lone neutron outside the supportive environment of an atomic nucleus is not immortal. Left by itself, it does not remain a neutron forever. It decays. That already tells us something important. A neutron is stable in some contexts and unstable in others. Even at the level of a single particle, permanence is conditional. Inside ordinary atomic nuclei, neutrons help provide stability because the strong nuclear interaction can bind protons and neutrons together. This interaction is powerful at very short distances, powerful enough to overcome the electric repulsion between positively charged protons. That is how nuclei exist at all. But if you ask whether you can just keep adding neutrons indefinitely to make larger and larger nuclei, nature again becomes fussy. Some nuclei tolerate extra neutrons, others do not. Push too far and they become unstable. The picture is not one of unrestricted assembly. There are allowed combinations and disallowed combinations, islands of stability and cliffs of decay. This means that when we ask how many neutrons can be stacked before reality breaks, we are not talking about a giant atomic nucleus in any ordinary sense. We are talking about pushing matter into a regime beyond normal nuclear structure, into a state where individual atoms cease to matter as atoms. Electrons are no longer orbiting neatly. Nuclei are no longer politely separated. Under crushing conditions, matter is forced into entirely new behaviour. One of the odd beauties of physics is that the same substance can become almost unrecognizable when pressure rises enough. Water can be ice or vapor or liquid. Carbon can be graphite or diamond. Matter inside a dying massive star can become something so dense that our everyday categories fail. And that brings us to the role of gravity, which in ordinary life is strangely modest. It keeps our feet on the ground, drops apples from trees, and ensures that dropped toast displays a level of confidence in butter, side-down outcomes that science has yet to improve. But gravity is the weakest of the fundamental interactions when considered at the level of individual particles. One neutron does not pull strongly on another in any way you would notice. Even a laboratory full of matter is held together far more by electromagnetic forces and quantum structure than by self-gravity. You do not need to calculate the gravitational collapse of your bookshelf. Your bookshelf has other problems, but that is not one of them. Only when matter becomes truly enormous does gravity begin to dominate. Stars are where gravity becomes a serious organizing force. A star is not a bonfire in space. It is a gravitational negotiation. Its own mass pulls inward, while pressure from hot material and energy generated in its core pushes outward. For most of its life, a star exists because those two tendencies are balanced well enough, but eventually that balance changes. Fuel runs low, pressure support weakens, the core can no longer maintain its old arrangement. Then collapse begins, and the deeper rules of matter are forced to reveal themselves. At lower masses, some stars end as white dwarfs, where a quantum effect involving electrons supplies the pressure that halts further collapse. That is already remarkable. A dead star held up not by burning, not by ordinary chemistry, but by quantum rules that prevent electrons from all occupying the same states. Yet even white dwarfs have a limit. Make the remnant too massive and electron-based support no longer suffices. Gravity squeezes harder. Electrons and protons are forced together. Neutrons become the main players. Matter passes into a new regime. What is so striking is that this process is not optional decoration in the cosmic story. It is central. The universe produces stars across a range of masses, and some of those stars are heavy enough that their deaths push matter through these extreme transitions. A core may briefly resist collapse, then plunge inward in a catastrophic implosion. The outer layers may rebound or be blasted away. Neutrinos flood outward. A supernova erupts, and at the center, depending on the mass and conditions, something survives. Sometimes a neutron star, sometimes not. This is where our opening question starts to acquire real shape. We're not imagining an engineer somewhere carefully stacking neutrons one by one with tweezers the size of galaxies. We're asking about what the universe itself discovers when gravity keeps compressing matter. How much neutron-rich matter can exist in a stable form? Where does neutron matter first become meaningful? Where does it fail? And why are those boundaries so important? There is also a philosophical pleasure in this kind of problem, though I promise not to become too philosophical about it. Physics often advances by asking what happens when you keep going. What happens if you cool something further, heat it more, compress it harder, enlarge it, shrink it, speed it up, strip it down? Everyday intuition is usually built in the middle range, where things are mild, but the universe is under no obligation to remain mild. Push any rule far enough, and you discover whether it is fundamental, approximate, emergent, or waiting to be replaced by a more interesting rule. With neutrons, the game is especially revealing because it forces quantum mechanics and gravity into close contact. Quantum mechanics governs the small, the probabilistic, the structured oddness of matter at microscopic scales. Gravity governs the large, the collective, the geometry of massive things. Most of the time, in most places, these two domains can be treated separately. Not perfectly, perhaps, but comfortably enough. Neutron stars are among the places where that comfort disappears. Here is matter compressed so far that the quantum behavior of particles determines whether a star-sized object can resist its own gravity. This is not a minor technical detail. It is one of the sharpest examples in nature of two great frameworks confronting one another. And the phrase reality breaks, though a touch theatrical, is not entirely unfair. It is not that the universe stops making sense, quite the opposite. It follows its rules with brutal consistency. But our ordinary picture of matter breaks. The idea of atoms as tiny solar systems breaks. The idea of solids and liquids as familiar categories breaks. Even our intuitive picture of pressure begins to wobble, because the pressure supporting a neutron star is not the sort of pressure you feel in a bicycle tyre or a steam engine. It is a deeply quantum resistance to compression, bound up with the fact that neutrons cannot all be pushed into the same quantum conditions. And yet even that extraordinary resistance is finite. So tonight we are really setting the stage for a story about limits. Not a gloomy story, though there will be black holes eventually and they do have a certain reputation. It is a story about thresholds, about what matter can endure, about how the universe uses extreme death to create future possibility. The balance is narrow enough that if it were substantially different, the cosmic inventory might look very strange indeed. Fewer neutron stars, more black holes, different supernova, different heavy element production, perhaps a universe poorer in some of the ingredients that later become geology, biology, and whatever it is that compels humans to watch long videos about astrophysics while wrapped in blankets. There is comfort, I think, in noticing that the grandest facts about existence often rest on balances that are not broad and forgiving but narrow and exacting. That can sound unsettling at first. One would rather imagine the universe as robust, endlessly tolerant, impossible to spoil, and in some ways it is, but in other ways it is delicately arranged. Change the wrong threshold and the later story changes too. This particular threshold, the one governing when compressed matter becomes a neutron star and when it collapses beyond one, is one of those quietly decisive features. We will move through that story carefully, first by getting to know the neutron itself more closely, because it deserves better than its usual supporting role in schoolbook diagrams, then by asking why small collections do not simply become permanent neutron lumps. From there, gravity will begin to matter more and more, until it becomes the dominant sculptor. We will see how stars reach the point where matter is crushed into neutron-rich form, what it means for atoms to effectively surrender, and why neutron stars can exist only within a limited range. After that comes the final tipping point, where too much mass means that even neutron matter is not enough. And from there, we can circle back to the larger consequence, the one hidden in the background all along, which is that this narrow balance is not a curiosity at the edge of astrophysics, but part of the machinery that makes a chemically rich and structured universe possible. For now, it is enough simply to hold the question in mind and let it settle. How many neutrons can you stack before reality breaks? Not as a riddle with a neat little number ready at the bottom of the page, but as a doorway into the way nature negotiates with itself. Too few and the arrangement is not stable. Enough and a neutron star is born. Too many and even that extraordinary state is overruled. Somewhere between impossibility and collapse lies a narrow zone where matter can briefly hold its ground against gravity. And in that brief resistance, whole chapters of cosmic history are written. A neutron is, on paper, a very modest sort of thing. It has no electric charge, no colour in the ordinary sense, no smell, no sound, and absolutely no concern for whether we find it easy to imagine. If protons tend to receive the more public role in schoolbook atoms, mostly because they help define what element something is, neutrons often arrive with less fanfare, as though they were merely there to keep the nucleus company and make sure no one gets too unruly. They are introduced almost politely. Protons are positive, electrons are negative, neutrons are neutral, and everyone nods as if the matter were settled. But that calm little summary hides a surprisingly strange object. The neutron is one of those pieces of nature that looks simple only from a respectful distance. Step closer and it becomes increasingly difficult to describe in plain everyday terms. It is not a tiny billiard ball, It is not a minuscule bead of stuff with a hard little shell. It is a quantum object, and like most quantum objects, it resists the kind of mental picture our brains would very much prefer to use. We like things that are somewhere, doing something, with edges and behaviour that stay put while we inspect them. The neutron, while real enough to help build stars and wreck any complacent assumptions we might have about matter, does not cooperate with that style of thinking. And yet, for all its strangeness, the neutron is deeply familiar in a quiet way. Nearly every atom heavier than ordinary hydrogen contains them. They sit in atomic nuclei beside protons, helping hold the nucleus together through the strong nuclear interaction, which is one of those force names that has the useful virtue of not being misleading. It is very strong. Over very short distances, it is powerful enough to overcome the electric repulsion between protons, which would otherwise be quite happy to shove each other apart. Without neutrons and the strong interaction that binds nuclear matter, atoms beyond the simplest sort would not remain assembled for long, and chemistry would be a very sparse and disappointing affair. So in one sense, the neutron is a stabilizer, a quiet contributor to structure, one of the reasons ordinary matter can have any richness at all. But in another sense, it is a warning sign that nature is more subtle than our first descriptions. Consider the fact that a neutron inside a stable atomic nucleus can remain there quite happily. While a neutron on its own is not permanent, a free neutron eventually decays. Left alone long enough, it transforms into other particles. That should already make us pause. This particle that helps stabilize nuclei is itself unstable in isolation. It is not a timeless, indivisible pebble. Its behavior depends on context. That dependence on context is one of the most important lessons in modern physics, though it rarely gets the dramatic appreciation it deserves. We tend to think of objects as having identities that travel with them unchanged. A chair is a chair whether it is in a kitchen or on a sidewalk. A spoon remains a spoon even if it is shamefully underused in the back of a drawer. But in particle physics and nuclear physics, what something does and whether it persists can depend very strongly on its surroundings. A neutron in a nucleus is not simply the same as a neutron drifting alone through space, with no companions and no nuclear binding to support it. Same particle, different situation, different outcome. This is one reason our central question becomes interesting so quickly. When we ask how many neutrons can be stacked before reality breaks, we are not asking about some perfectly obedient building block that remains unchanged no matter what we do. We are asking about a particle whose very stability shifts with circumstance, whose role in matter changes under pressure, and whose collective behaviour becomes dramatically different when gathered into enormous numbers. The neutron is not just a unit in a cosmic inventory. It is one of the places where the universe quietly informs us that identity in physics is often relational. Now, if we linger for a moment with the neutron itself, one of the first notable things about it is its mass. Not because it is enormous, of course. On human scales, it is absurdly tiny. To call it lightweight would be generous to the point of comedy, and yet within the subatomic world its mass matters a great deal. It is slightly heavier than the proton, not by much, but enough to shape the behaviour of ordinary matter. If the balance were reversed in a different way, the stability of atoms would change radically. The detailed architecture of chemistry, and therefore the possibility of stars, molecules, rocks, oceans, and thoughtful insomniacs, would be different. It is another of those places where a very small numerical difference carries a very large consequence. There is something wonderfully awkward about that. We often imagine the foundations of reality as resting on grand obvious principles, enormous truths carved in bold cosmic letters, but again and again the universe turns out to depend on tiny imbalances, small offsets, narrow thresholds, and quantitative details that look almost petty until you realise they control everything downstream. The neutron being just a little heavier than the proton is one of those details. It contributes to why free neutrons decay while free protons do not. It influences nuclear stability. It helps determine what matter can do over long stretches of cosmic time. a slight weight difference in the world of particles, and the visible universe takes shape accordingly. But even saying that a neutron has a mass can sound more straightforward than it really is. What is the neutron made of? One might hope for a simple answer and then be disappointed in a scientifically healthy way. The neutron belongs to a family of particles called baryons, and it is composed of quarks, specifically 1-up quark and 2-down quarks. That sounds tidy enough until one remembers that quarks are not little marbles hiding inside like peas in a shell. They are themselves quantum entities bound together by gluons through the strong interaction described by quantum chromodynamics, which is a phrase that always sounds as though it ought to come with a warning label and a very serious chalkboard. Inside the neutron there is motion, interaction, confinement, and an ongoing exchange of energy that makes the very idea of a fixed, simple interior rather slippery. Much of the neutron's mass does not come simply from the bare masses of its constituent quarks. It comes from the energy of the interaction itself. In other words, mass here is not just stuff in the naive sense. It is bound up with energy, with motion, with the restless quantum activity inside the particle. The neutron, which seems from a distance like a small neutral lump, is in fact a dynamic system of confined quarks and gluons, whose properties emerge from that complicated internal life. That too matters for the larger story, because when we later speak about matter being crushed inside a neutron star, the question of what exactly a neutron is, and whether it remains the relevant description under extreme density, becomes less academic and more urgent. At moderate conditions, speaking of neutrons is sensible. At higher and higher densities, some physicists suspect that matter may pass into forms where even neutrons no longer remain intact in the familiar sense, and quark-level behaviour may become impossible to ignore. So the strange little weight of a neutron is not merely an introduction to acute subatomic character, it is the beginning of a much larger issue about what matter becomes when squeezed beyond ordinary categories. Still, before heading toward those more exotic possibilities, it is worth appreciating just how odd the neutron already is within ordinary nuclei. Think of an atomic nucleus. It is tiny beyond casual comprehension, and yet it contains most of the mass of the atom. Electrons occupy a much larger region around it, but the dense core sits at the centre holding protons and neutrons together. Inside that nucleus, the neutron plays several roles. It contributes mass, certainly. It contributes to nuclear binding. It helps spread out the influence of the strong interaction without adding electric repulsion, because unlike the proton, it carries no positive charge. This makes it exceptionally useful in building larger nuclei. Add too many protons alone and the electric repulsion becomes a serious problem. Add neutrons and you can often strengthen the nucleus without worsening that particular tension. But there is no unlimited generosity here. Neutrons help, yet too many neutrons can also destabilize a nucleus. Stability is not simply a matter of piling them in until the container looks full. Nuclear structure has shells and configurations and balance conditions of its own. Some nuclei are stable, some are radioactive, some decay in moments, some last longer than stars. This is one of the reasons one cannot simply imagine creating larger and larger ordinary neutron-rich nuclei forever. There are boundaries, drip lines, instability regions. Matter allows some arrangements and rejects others, and perhaps this is the right moment to note that the word stack, charming as it is, can be a little misleading. Neutrons are not stacked in the way books are stacked, or dishes are stacked, or badly folded, laundry is stacked in a state of mutual denial. In the quantum world, particles do not line up in clean visible layers waiting for gravity to embarrass them. They occupy allowed states. They are described by wave functions. Their collective arrangements depend on quantum statistics, interactions, confinement, and energy minimization. So when we say stack, what we really mean is force more and more neutrons into a shared physical system and ask what sort of object, if any, results. That question leads naturally to another peculiar property of neutrons. They belong to the class of particles called fermions. Fermions are subject to a strict rule known as the exclusion principle. Two identical fermions cannot occupy exactly the same quantum state. This is one of the reasons matter has structure at all. It is why electrons in atoms arrange into shells rather than collapsing into one indistinguishable heap around the nucleus. It is why white dwarfs can resist gravity through electron degeneracy pressure. And it is why neutrons, when packed together in extraordinary densities, can provide a pressure of their own. Not because they are pushing like compressed springs in a mechanical toy, but because quantum mechanics refuses to let them all collapse into the same conditions. The exclusion principle is one of those rules that sounds technical until you realize it is partly responsible for tables, mountains, stars, and your current ability not to fall through the floor. Without it, matter would behave in a profoundly different way. When applied to neutrons, it becomes one of the major reasons a neutron star can exist at all. But it is also not an unlimited shield. The pressure that arises from fermionic crowding can resist gravity up to a point. Beyond that point, the protest is no longer enough. So already within the neutron itself and its classification, we have several ingredients for the larger story. It is neutral, which makes it useful in dense matter because electric charge is not constantly blowing the whole arrangement apart. It is slightly heavier than the proton, which affects stability and decay. It is a composite quantum object whose mass emerges largely from internal interaction energy. It is a fermion, which means large collections of neutrons are governed by exclusion-based pressure. It can be stable in a nucleus but unstable on its own. None of that is remotely boring, though the neutron usually presents itself with such modesty that one almost feels guilty for being impressed. There is also the matter of scale, and here the neutron begins to teach one of physics's favourite lessons. Small does not mean simple. In daily life, large things tend to feel more consequential. Mountains matter more than pebbles. Oceans matter more than raindrops. A collapsed bookshelf demands more immediate attention than a single book placed askew. But in fundamental physics, the small scale is often where the real rules hide. A neutron is tiny beyond all ordinary sensory imagination, yet the behaviour of immense astrophysical objects can depend on the collective properties of particles exactly like it. The fate of a stellar core may be decided by what neutrons are allowed to do under compression. This is one of the delights of science, that the tiny and the vast are not separate domains with a polite fence between them. They're connected in ways that are at once exact and astonishing. Take a neutron star, for instance, though we will reach it properly in time. Its existence depends on the accumulated behaviour of roughly astronomical numbers of neutrons packed into a region the size of a city. But the laws that govern that star are not invented anew at stellar scales. They arise from particle properties, nuclear interactions, quantum rules, and relativistic gravity. The small does not disappear when the large begins. It becomes destiny. And yet, as important as the neutron is, one must be careful not to over-romanticize it as some ultimate indivisible foundation. Physics has a way of punishing anything that sounds too final. Once upon a time, atoms themselves were thought indivisible. Then came electrons, nuclei, protons, neutrons, then quarks, gluons, and quantum fields. The neutron is fundamental enough for many purposes, but not final in every sense. This matters because when matter is squeezed harder and harder, the level at which the best description changes. There are environments where talking about atoms makes sense, others where only nuclei matter, others where neutrons dominate, and perhaps deeper still, environments where even the neutron yields to a more fundamental description. That possibility gives our question its delicious instability. How many neutrons can you stack before reality breaks? Well, even the noun neutron may eventually become negotiable if conditions grow extreme enough. Reality, far from breaking carelessly, keeps changing the terms of the discussion. First it says you cannot have this many neutrons in an ordinary nucleus. Then it says under sufficient gravity, neutron-rich matter can exist. Then it says beyond another threshold, perhaps even neutron matter is no longer the final picture. The universe is less like a wall with a single sign saying stop, and more like a sequence of gates, each requiring a deeper language than the last. For now, though, we remain with the neutron as it appears in the relatively familiar world of nuclear physics. Even there, it behaves with an odd mix of loyalty and independence. Bound into nuclei, it helps support structure. Freed from those bonds, it wanders only temporarily before decaying. Shot into materials, neutrons can be extraordinarily useful probes because their lack of electric charge lets them penetrate where charged particles would be diverted. They reveal magnetic structure, atomic arrangement, and hidden internal properties of matter, so the neutron is not only a component of matter but also a tool for studying it. The quiet one in the room turns out to be the one who notices everything. There is something pleasing in that, perhaps because it rescues the neutron from its role as a mere sidekick. The proton gets to define the element, the electron gets chemistry and electricity and all the excitement of bonds and currents and glowing screens. The neutron seems, at first glance, almost administrative, but remove it and many nuclei vanish, increase its importance, and whole stars are held up by quantum rules associated with it. Use it cleverly, and it becomes an instrument of discovery. It is one of the most unassuming essential things in nature. One can also sense, even at this stage, why neutron matter is not going to behave like ordinary solid material. In everyday matter, electric forces dominate the structures we know best. Atoms form lattices, molecules make bonds, electron clouds determine shapes, surfaces, and texture. In neutron-rich extreme matter, much of that ordinary architecture is gone or altered beyond recognition. Neutrality changes the rules. Quantum crowding becomes central. Nuclear interaction and gravity take over from the chemical gentilities of the periodic table. Asking what a neutron weighs, then, is not merely about assigning a number. It is about identifying one of the raw ingredients that can enter a regime where the normal world stops being a useful guide. And perhaps that is the deeper reason this modest particle deserves a slow introduction. It sits right at the border between the world we think we know and the world that only appears when stars die badly enough. It belongs to ordinary nuclei, yes, but it also belongs to supernova remnants, to neutron stars, to the threshold before black holes. It is both domestic and extreme. You carry atoms containing neutrons in your body this very moment, and yet those same kinds of particles gathered under gravity in impossible numbers can produce one of the densest known forms of stable matter in the universe. That is quite a career for something often described in a sentence and a half. So when we speak of the strange little weight of a neutron, the strangeness is not only in its mass or neutrality or internal structure, though all of those are peculiar enough. The deeper strangeness is that such a small object can sit at the centre of one of the most important balances in astrophysics. A little heavier than a proton, neutral but not simple, stable in company and unstable alone, made of quarks but often acting as a practical whole, obedient to quantum exclusion yet capable of joining vast dense assemblies, the neutron is less a tiny bead of matter than a compact lesson in how subtle nature can be. All of this prepares us for the next difficulty, because knowing what a neutron is does not yet explain why you cannot simply gather a modest clump of them and call it a day. One might imagine that if neutrons are so central to dense matter, then surely a few thousand or a few million or a conveniently suitcase-sized amount ought to form some durable neutron object. But nature is not so accommodating. Small collections do not behave like miniature neutron stars. In fact, one of the crucial surprises is that neutron matter requires conditions far more extreme than casual intuition would guess. The neutrons, despite all their importance, do not simply agree to become a stable, self-contained lump on command. That reluctance is where the story starts to become even more interesting. At first glance, it seems like the problem ought to be simple. If neutron stars are made mostly of neutrons, then why not begin on a much smaller scale and work upward? Why not imagine taking a few neutrons, then a few more, then a few more after that, gently gathering them into a little lump of neutron matter, the way one might roll snow into a ball. Start modestly, perhaps with something pebble-sized, then larger still. and eventually one arrives at a neutron star with a certain sense of orderly progression. It sounds almost reasonable, and that is exactly why it's so misleading. Nature, as it turns out, is not remotely interested in giving us neat little chunks of neutron matter on ordinary scales. Tiny clumps refuse to become neutron matter for a whole collection of reasons, and those reasons go straight to the heart of what matter is allowed to do. This is one of those places where our everyday instincts lead us gently and confidently in the wrong direction. We are used to thinking that if a material exists in large form, then smaller samples of it should exist too. A lake can become a puddle, a boulder can become a stone, a loaf can become a crumb. If there are neutron stars, surely there can be neutron rocks, and yet there are not, at least not in the way that thought suggests. The first difficulty is that neutrons on their own are not the sort of deeply committed companions one might hope for. A free neutron is unstable. Outside the protective and binding environment of a nucleus, it does not remain a neutron forever. Given enough time, it decays. That fact alone already makes small neutron collections inconvenient. If you imagine trying to make a tiny object out of free neutrons, you're starting with ingredients that do not particularly enjoy being left unsupervised. They are much happier, or at least much more durable, when bound into atomic nuclei than when wandering alone in empty space. Now, one might object that perhaps neutrons in a group could bind one another strongly enough to remain together, forming a stable droplet of neutron matter. After all, the strong nuclear interaction is very strong, which is an admirably honest name by the standards of science. Protons and neutrons do bind in nuclei. Why should neutrons not simply bind to each other in arbitrarily large neutral collections? But here the rules become more selective than the name strong might lead us to expect. Nuclear binding does not mean unlimited permission. It is not some universal glue that sticks everything to everything else forever. It depends on quantum states, energy balance, particle identity, and the details of how many neutrons and protons are involved. In ordinary nuclei, neutrons are not usually alone. They are part of a mixed system with protons, and that mixture matters. Protons and neutrons together can form stable nuclei because the strong interaction binds them, while the overall arrangement finds a workable balance between attraction, quantum structure, and the repulsive electric force among protons. Neutrons help by contributing to the strong binding without adding electric repulsion. That makes them excellent stabilizers within nuclei. But a collection of only neutrons is a much less cooperative proposition. For very small numbers, the situation is especially unkind. Two neutrons do not form a stable bound pair. One might imagine them as a sort of minimalist nucleus, a tiny neutron duet minding its own business in the vacuum, but nature declines the offer. The pairing is not bound in the ordinary stable sense. Add more neutrons and the problem does not magically solve itself in any simple way. There may be fleeting resonant states, brief and delicate arrangements that appear in experiments under special conditions, but these are not stable lumps you can put on a shelf and admire. Tiny neutron clusters tend not to settle into long-lived self-bound objects. This phrase self-bound is important. Ordinary materials are self-bound by electromagnetic interactions and chemistry. A rock does not need its own gravity to remain a rock. A spoon does not rely on being planet-sized in order to continue existing as cutlery. Its atoms and electrons do the necessary structural work locally. Neutron matter on small scales does not enjoy that luxury. It is not self-bound in the way familiar matter is. It typically requires external pressure, and in the cosmic version of that story, the external pressure is gravity, provided on a scale so vast that the words external pressure begin to sound almost too gentle for the job. That is one of the central surprises here. Neutron matter, in the neutron star sense, is not simply a substance like iron or ice, waiting to be sampled in smaller pieces. It is more like a state of matter that becomes possible only under extreme confinement. Remove the confinement and the state is no longer favoured. The tiny clump does not sit there loyally maintaining neutron star conditions out of principle. It relaxes, rearranges, decays, and generally behaves like matter escaping an unnatural situation. There is a useful comparison here with white dwarfs, because white dwarfs offer a slightly less extreme version of the same lesson. A white dwarf is held up by electron degeneracy pressure, another quantum effect involving fermions refusing to occupy identical states. Yet one does not chip off a chunk of white dwarf material and bring it home in a bucket. If somehow separated from the crushing environment of the star, that matter would not remain in its white dwarf state. It would expand and reorganize. A neutron star is even more demanding. Its matter exists as it does because gravity has forced it into that arrangement. The state is not casually portable, but let us slow down and ask why the neutrons do not simply cling together anyway. Part of the answer lies in energy. Physics is, among many other things, a discipline about what configurations are energetically favoured. A system tends to settle into states of lower total energy when it can. For small collections of neutrons, a pure neutron lump is often not the preferred arrangement. There are lower energy outcomes available, including decay and rearrangement into other particles or into ordinary nuclei if protons and electrons are part of the larger context. Matter is not trying to frustrate us personally, though it can feel that way. It is simply following the route that the governing laws and energy balances permit. Another part of the answer lies in quantum structure. Neutrons are fermions, and fermions do not all pile into one cosy state together like sleepy cats on a blanket. They must occupy different quantum states in a large, dense system that leads to degeneracy pressure, which can resist further compression. But in a small system, it also means you cannot assume the neutrons will neatly settle into some compact bound object without paying energetic costs. The available states, the interaction energies, and the details of the nuclear force all matter. Sometimes when matter refuses to assemble the way we imagined, it is not because there is too little attraction. It is because the whole quantum bookkeeping turns against us. There is also the awkward issue that the strong interaction is short-ranged and subtle. This is not glue spread evenly through space. It is powerful at nuclear distances and highly dependent on the exact arrangement of particles. In nuclei, the balance of proton and neutron numbers matters. Shell effects matter. Pairing matters. The neutron-rich edge of nuclear stability is not an open frontier stretching indefinitely onward. It has boundaries. Beyond certain neutron numbers for a given proton count, extra neutrons are no longer bound and simply drip out. That phrase, neutron drip, has a curious softness for something so fundamental as though the cosmos had a leaking pipe problem. But it marks a very real limit. Add enough neutrons and they stop staying put in ordinary nuclei. This is a hint of what happens on larger scales. If neutrons are not bound in ordinary nuclei beyond certain limits, then a purely neutron object on modest scales is already in trouble. There is no stable chain of ever larger neutron-only nuclei leading smoothly to neutron star matter. There is instead a break between familiar nuclear matter and the matter found in neutron stars. That break is bridged not by ordinary nuclear assembly, but by catastrophic gravitational collapse. This is one reason the birth of a neutron star is such a violent business. You do not gradually gather neutron matter with patient craftsmanship. You create it when a massive star runs out of better options. Its core collapses so dramatically that matter is forced through thresholds it would never cross under ordinary conditions. Electrons are squeezed into protons. Neutrinos are emitted in enormous numbers. Atomic identities lose their usefulness. A dense neutron-rich core appears because the pressure is overwhelming, not because neutrons calmly preferred that arrangement from the start. There is a curious emotional lesson in this, if one is allowed a small emotional lesson in the middle of nuclear astrophysics. Some structures in the universe exist because they are naturally easy, the way a raindrop forms or a crystal grows. Others exist only because conditions become so extreme that matter has no more comfortable choice. Neutron matter belongs largely to the second category. It is not the relaxed posture of matter. It is the posture matter adopts when gravity has become impossible to ignore. That is also why the idea of a neutron pebble is so hopelessly romantic. A pebble suggests something self-contained, durable, and portable. It suggests that the material is happy in that state, and can remain so with no immense external demands. But neutron matter is not like that. Tiny clumps do not become stable neutron pebbles because they lack the vast inward pressure that makes neutron-rich dense matter favourable in the first place. Without that pressure, the system tries to find another arrangement, and it usually succeeds. One can push this further and ask what would happen if one could somehow carve out a small chunk from a neutron star. It is the sort of question physicists enjoy because it sounds straightforward and then collapses into complications almost immediately. The answer depends on exactly what one imagines being preserved during the extraction, which is already suspicious. But broadly speaking, once removed from the crushing gravitational environment, that matter would not remain as a neat neutron star fragment. It would decompress violently, rearrange, and cease to resemble its former state. Matter that exists only because it is trapped under immense pressure tends to behave rather dramatically when the trap is opened. This helps explain an important distinction between materials and states of matter. We casually use the word material for almost anything, but some things are only meaningful under particular conditions. Steam is water, yes, but it depends on pressure and temperature. Plasma depends on ionization conditions. Degenerate matter depends on density. Neutron star matter is a state that belongs to an environment, not a substance one can treat like a mineral sample. Tiny clumps refuse to become neutron matter, partly because neutron matter is not just about composition, it is about circumstances. There is yet another layer to the problem, and this one concerns the competition between different forms of pressure and binding as matter grows denser. In ordinary solids and liquids, electromagnetic structure dominates. In nuclei, the strong interaction governs much of the local organisation. In neutron stars, gravity becomes the grand enforcer, pushing matter into densities where quantum degeneracy and nuclear interactions respond collectively. But on small scales, gravity is laughably weak. A tiny clump of neutrons has almost no self-gravity at all. It cannot compress itself meaningfully. It cannot force itself into the regime where neutron star matter makes sense. This is crucial. Gravity is not merely a supporting actor here. It is one of the main reasons neutron matter exists on stellar scales and not on tabletop scales. That statement is easy to say and surprisingly difficult to absorb intuitively, because gravity feels so universal in daily life. It is always there, always competent enough to pull dropped keys into inaccessible corners and to make climbing stairs a mildly moral experience. But at the level of small collections of particles, gravity is so feeble as to be almost irrelevant compared with the other interactions. To make gravity matter, truly matter, you need huge masses, you need stars, you need collapse, you need enough material that the inward pull becomes a structural fact rather than a decorative detail. So small neutron clumps are trapped in a sort of no man's land. They are too small for gravity to help. They are not naturally self-bound in the necessary way. Free neutrons decay. Pure neutron systems do not settle into stable little droplets under ordinary conditions, and the energetic and quantum rules do not favour the kind of compact neutral lump our imagination would so much like to picture. The result is that there is no gentle staircase from a few neutrons to a neutron star. There is a gulf, and gravity builds the bridge only when the masses become enormous. This is also why the phrase neutron matter can be deceptive if taken too casually. One hears it and imagines matter made of neutrons, which is true enough as a starting point but incomplete. Neutron matter in the astrophysical sense means matter under such density and pressure that neutrons dominate the composition and quantum behaviour of the system. It does not mean any arbitrary gathering of neutrons, however small. That's like saying a hurricane is just air, and then expecting a desk fan to qualify. Composition matters, yes, but so do scale, confinement and collective behaviour. There is a certain elegance in the refusal, though perhaps elegance is not the first word one reaches for when the universe keeps declining one's hypothetical neutron paperweight. Tiny clumps refuse to become neutron matter because the laws are consistent. They are not allowing just enough to tease us and then changing their minds at random. The same deep principles that let neutrons stabilize nuclei also limit pure neutron binding. The same quantum rules that later help support a neutron star do not magically create small, stable neutron droplets without the corresponding conditions. The same gravity that will one day force a collapsing stellar core into a neutron-rich state is powerless to do anything of the sort for a microscopic handful. And this refusal is not a minor inconvenience in the cosmic story. It means that neutron stars are not ordinary extrapolations of nuclear matter. They are exceptional outcomes, created only when stellar collapse drives matter into a rare and violent regime. That helps make them so important. If neutron matter were easy, if little neutron lumps formed casually, the universe would look very different. But it is difficult, and because it is difficult, stars must reach extraordinary endpoints before such matter appears. There is also something slightly humbling here. Humans are very good at taking words too literally. If matter in a neutron star is mostly neutrons, then surely neutrons are the essence and everything else is detail. But physics rarely allows such shortcuts. Collective states depend on conditions. Many of the most interesting things in nature are not just collections of ingredients, but arrangements made possible only in narrow domains. Superconductors need special temperatures, lasers need population inversions, neutron matter needs crushing pressure. Remove the condition and the phenomenon vanishes. So by now our simple image of stacking neutrons has become somewhat less innocent. It is not a child's building game with increasingly dense blocks. It is a question about whether pure neutron systems can bind themselves without enormous outside help, and the answer is mostly no. Tiny clumps refuse because free neutrons are unstable, because pure neutron binding is weak or absent for small systems, because quantum mechanics imposes structure rather than letting everything collapse into one convenient nugget, and because gravity on small scales is too feeble to force the issue. That leaves us with an important next step. If tiny clumps cannot do it on their own, then what changes when enough matter gathers for gravity to become serious? At what point does the conversation stop being about impossible little clusters and start becoming about stellar cores, collapse, and the conditions under which neutron matter is no longer a fantasy but a consequence? The answer, naturally, is that gravity finally joins the conversation, and when it does, the tone changes rather dramatically. For a surprisingly long stretch of the story, gravity is almost a bystander. That can feel odd to say, because gravity is the force most familiar to us. It keeps planets in orbit, shapes galaxies, gathers stars, and gives every dropped object a firm opinion about where the floor is. It is the great collector of the universe, the quiet accountant of mass. And yet, when we talk about small clumps of neutrons, gravity barely matters at all. A few neutrons do not care much about their own gravitational attraction. Neither do a few trillion, or a mountain or a planet in the sense relevant here. On small and moderate scales, matter is governed mainly by other interactions. Electromagnetism organizes atoms and chemistry. The strong nuclear interaction binds nuclei. Quantum mechanics dictates what states particles may occupy. Gravity, though always present, is too weak to force exotic arrangements out of ordinary material. Then the scale changes. This is one of the most important turning points in the whole discussion. If tiny clumps refuse to become neutron matter, because nothing compels them to do so, then the obvious next question is what sort of compulsion nature actually uses. The answer is gravity, but not gravity in its mild, everyday mood. Not gravity as the thing that nudges rain downward, or makes staircases feel like a poor life choice by the third flight. We mean gravity as it appears when huge amounts of mass are crowded together, when an entire star is involved, when matter has nowhere left to retreat and no gentler arrangement available. Only then does gravity stop being background scenery and become the chief negotiator. A star is, in many ways, a long argument between gravity and pressure. That is the simplest useful picture, and it is worth holding on to because the rest of the story grows from it. Gravity pulls inward. Pressure pushes outward. As long as those two are balanced well enough, the star survives in a more or less stable form. Most of a star's life is spent in this compromise. In its core, nuclear fusion releases energy. That energy supports pressure. The pressure resists gravity. Gravity keeps the core hot and compressed enough for fusion to continue. It is not a peaceful arrangement exactly, but it is a successful one. The star shines because inward collapse and outward pressure are locked in an ongoing stalemate. This may sound rather dignified, but stars are not dignified for purely noble reasons. They are dignified because the alternatives are dramatic. If gravity ever gains too much of the upper hand, the core contracts. That contraction heats the core and can trigger new kinds of fusion, depending on the star's mass. In lighter stars, this can happen in stages and eventually settle into a quieter ending. In heavier stars, things become much less forgiving. The fuel sequence advances. The core composition changes. The pressure support that worked before becomes less and less effective, and eventually the star reaches a point where the ordinary methods of resisting gravity are no longer sufficient. What makes this so crucial for our neutron question is that gravity does not merely squeeze matter harder in a general way. It changes which forms of matter are possible. Under ordinary conditions, atoms are roomy structures by nuclear standards. Electrons occupy a cloud around a tiny nucleus, and most of the atom is effectively empty space if one insists on that old but still useful phrase. In ordinary solids, those atoms sit in organized patterns, held apart and arranged by electromagnetic behavior. Matter, in other words, has space to breathe. Gravity inside a normal rock or even a planet does not eliminate that architecture. A planet may be compressed by its own weight, yes, but not enough to erase atomic identity wholesale. Stars are different. Their central conditions are much harsher, and when a massive star nears the end of its life, the core can become so dense and pressured that atomic structure is no longer sacred. Electrons are pushed into more and more energetic states. The matter becomes degenerate, meaning quantum crowding begins to matter deeply. At first, electron degeneracy pressure can offer resistance. This is the same broad principle that supports white dwarfs, where electrons, being fermions, refuse to all occupy the same state. The pressure is not thermal in the familiar sense. It does not depend simply on heat. It comes from the quantum fact that you cannot keep shoving identical fermions into the same conditions indefinitely without paying an energetic price. That is already remarkable. A dead star can resist collapse not by burning, not by chemical structure, not by any ordinary springiness, but by quantum mechanics saying no to further crowding. Yet even this refusal has limits. If enough mass is piled onto such a core, gravity continues to intensify. Electrons are forced into still higher energy states. Their pressure rises, but not fast enough forever, and there comes a point where electron-based support can no longer hold the line. This is where gravity truly joins the conversation in the way our story needs. Before this point, one could still imagine that matter, though stressed, remained within some altered extension of ordinary atomic and nuclear life. Beyond this point, gravity begins to erase categories. Electrons are squeezed so hard that they are driven into protons. The result is a flood of neutrons and neutrinos. Matter becomes far more neutron-rich. The old distinction between nuclei surrounded by electrons and some background space for them to inhabit starts to collapse. The core is being pushed into a state that would never arise casually. Gravity is no longer asking politely whether matter might try a denser arrangement. It is forcing the issue. There is something almost procedural about the way the universe arrives here. It does not begin with neutron stars because neutron stars are interesting. It begins with stars, with fusion, with pressure support, with the gradual exhaustion of easier energy sources. Then the star keeps increasing the stakes, burn lighter elements, then heavier ones, each stage shorter than the last in the most massive stars. The core composition changes, the available pressure mechanisms shift. The star, having spent millions of years balancing gravity with energy production, suddenly finds that its old economic model no longer works. Gravity notices. Gravity has been waiting the whole time. In a very real sense, gravity is patient. That may sound suspiciously literary, but astrophysics rewards the thought. Gravity does not need urgency. It can wait through the long, bright life of a star. It can tolerate fusion holding it off for ages. But once the pressure support weakens enough, gravity resumes the inward motion it had wanted from the beginning. And because so much mass is involved, once collapse begins, it can proceed with terrifying speed. This is the key to why tiny neutron clumps are impossible, while neutron stars are real. The missing ingredient is not some secret neutron glue, available only to larger systems in a mystical way. The missing ingredient is scale, and scale means gravity. Only when enough mass is present does self-gravity become strong enough to compress matter to neutron star densities. Small systems cannot do that. They have the neutrons perhaps, or at least can imagine them, but not the inward force needed to make neutron-rich matter the favoured state. Massive stellar cores can. One of the more humbling aspects of this story is how absurdly much matter is required before gravity begins to compete with the microscopic rules in this particular regime. Human intuitions about weight and compression are shaped by chairs, buildings, mountains, perhaps the occasional regretfully overpacked suitcase. We know that stacking more mass increases pressure. That much feels straightforward. But the amount of mass needed to force matter out of atomic form and into dense degenerate states is beyond all ordinary experience. It is not a very big mountain. It is not even a planet. It is a stellar core. Gravity only joins this conversation when the meeting room is truly enormous. And even then, it does not arrive alone. When gravity becomes dominant, it drags relativity into the room as well. This is important because once matter becomes extremely dense, Newton's gentle version of gravity begins to lose some of its adequacy. Strong gravitational fields and very compact objects require a relativistic description. Time, space, pressure, and energy all become more tightly entangled than our ordinary language suggests. Pressure itself contributes to gravity and general relativity. That is a deeply unnerving fact if one likes one's intuitions tidy. The very thing helping resist collapse also adds to the gravitational field under the full theory. Reality does not always separate roles as cleanly as we might. Still, before we get to the most extreme compact objects, it helps to stay with the core of a massive star just as collapse begins. The central region is no longer supported by ongoing fusion in the old way. Thermal pressure is losing its authority. Electron degeneracy cannot carry the burden indefinitely. Gravity compresses the core. As it contracts, densities rise. Electrons become more energetic because they are squeezed into fewer available states. Eventually conditions become favourable for electrons and protons to combine, producing neutrons and neutrinos. The neutrinos escape or try to, carrying away energy. The matter becomes neutron-rich. And the collapse, rather than halting gently, often accelerates into a catastrophic implosion. This is not a slow settling. It is one of the most violent transitions in astrophysics. The outer layers of the star have not had time to calmly update their expectations. The core plunges inward. The density climbs rapidly. Nuclear matter is approached. And then, in successful cases, something remarkable happens. The inward collapse can be halted, at least for the core remnant, because neutron-rich matter becomes stiff enough, through quantum effects and nuclear interactions, to resist further compression. The core rebounds or stiffens, shock waves form, neutrinos pour through the star. The supernova emerges from this bewildering sequence. So gravity's role is not merely to compress matter until neutrons appear, it is also to create the circumstances for the entire supernova drama. Without gravity pushing the core beyond the limit of lesser forms of pressure support, there would be no neutron star remnant in the usual sense, no such collapse, no corresponding explosion pattern. Gravity is both destroyer and maker here. It destroys the old atomic structure, the old equilibrium, the old life of the star. In doing so, it enables a new form of matter and a spectacular redistribution of stellar material into the cosmos. This dual role matters because it begins to show why the neutron star window is so precious. If gravity were weaker in this context, perhaps the collapse would not reach neutron matter so decisively. If stronger, or if the mass were too large, the collapse would not stop there at all. The star would not leave behind a neutron star, but continue on toward a black hole. So when gravity joins the conversation, it is not simply speaking louder. It is determining which phase of matter can briefly stand against it and for how long. There is also an aesthetic pleasure in the fact that gravity, the weakest interaction at the particle level, becomes the master sculptor on cosmic scales. This reversal is one of nature's favourite tricks. For a single neutron, gravity is negligible. For a neutron star, gravity governs everything. The particle that did not care at all about its own weight in isolation becomes part of a collective object whose fate is determined by the accumulated weight of unimaginable numbers of similar particles. A neutron does not fall into neutron matter because of its own tiny gravity. It falls into neutron matter because enough of its companions are present to make gravity irresistible. And this is where one begins to appreciate the difference between local rules and global consequences. Locally, the neutron obeys quantum mechanics and nuclear interaction rules. Globally, a whole star's worth of matter creates a gravitational environment in which those local rules produce a new state. The state is not encoded in any single neutron. It emerges from the marriage of microscopic law and macroscopic mass. That is why neutron stars feel so profound. They are not just dense objects. They are places where the very small and the very large are forced into direct cooperation. Of course, gravity's entrance is not universally triumphant. It has to contend with the fact that matter is not infinitely compressible. Quantum mechanics pushes back. Nuclear forces push back. The behaviour of dense matter becomes increasingly important and increasingly uncertain in detail. What exactly is the pressure of neutron-rich matter at a given density? How do the constituents behave at the deepest layers? Does the matter remain mostly neutrons throughout, or do more exotic states arise? These are not decorative questions. They determine how large or small a neutron star can be, how it responds to added mass, how it deforms, cools, and perhaps eventually collapses. Yet even without resolving every microscopic uncertainty, the broad picture is clear enough to guide us. Gravity must first become strong enough to overwhelm the less extreme supports. It must compress matter into a regime where neutron-rich dense matter becomes favoured. Then, if the total mass lies within a certain range, the resulting object can survive as a neutron star. Not because gravity has been defeated in any permanent sense, but because a temporary truce has been established. Gravity pushes inward. Neutron degeneracy and nuclear interactions push back. Neither side gets everything it wants. The result is a compact star. There is something almost judicial in that. Gravity finally joins the conversation, but it does not instantly win every case. It forces a higher court of physics to convene. Quantum mechanics is called. Nuclear physics is called. Relativity presides over the room with increasing sternness, and the verdict depends on the total mass and the properties of dense matter. For some stellar cores, the sentence is neutron star. For others, black hole. The difference is not whimsical. It is written into the narrow balance among these laws. That narrowness is worth emphasizing because it is easy to imagine the universe as having wide, forgiving categories. This object is a star, that one a neutron star, that one a black hole, as if each were just a different shelf in a cosmic cupboard. In reality, the transitions are hard won. A neutron star exists only because gravity is strong enough to create it and not yet strong enough to destroy it completely. It is born in the middle of an argument that could have gone differently. Too little compression and ordinary nuclear matter remains the limit. Too much compression and no stable neutron star survives. Gravity's joining the conversation is therefore not the end of the question, but the beginning of a narrower and more dangerous phase of it. There is also a subtle lesson here about why extreme astrophysics often feels more real than abstract once one sits with it for a while. At first, the idea of stellar collapse into neutron-rich matter sounds remote, perhaps even theatrical. But the mechanism is brutally concrete. A star runs out of effective ways to support itself. Gravity compresses the core, electrons and protons combine, neutron-rich matter appears, pressure support changes character. Either collapse halts at a compact remnant or it does not. This is not a symbolic sequence. It is a physical one, repeated across the universe, responsible for some of the most important leftovers in cosmic history. And those leftovers matter. A neutron star is not just an endpoint. It is also a source of insight, of gravitational waves when merged, of intense magnetic activity in some cases, of clues about the behavior of dense matter. It is part of the cycle through which stars enrich the universe. So when gravity finally joins the conversation, it does more than solve our earlier problem of why tiny neutron clumps fail. It opens the door to everything that follows, from supernovae to remnant masses to the ultimate question of how much neutron-rich matter can be held before the truce fails. For the moment, though, we are still at the threshold. Gravity has become relevant. Atomic structure is beginning to surrender. The star is no longer living by ordinary rules. The matter in the core is being driven toward a state unlike anything found in daily life. A state where atoms no longer maintain their familiar identities and neutron-rich dense matter begins to take over. That is the point at which the story turns from why small systems cannot do it to how a star actually manages to. And once that process is underway, the next thing we need to understand is what it really means for ordinary matter to be crushed so completely that atoms, in any recognizable sense, give up. A star spends most of its life pretending that balance is ordinary. From a distance it looks calm enough, a bright point in the dark, steady and self-contained, as though shining was simply what it does in the same casual way a lamp glows when switched on. But a star is never merely glowing. It is enduring. It is holding itself up against its own weight every moment of its existence. Gravity pulls inward without rest, and the star answers with pressure pushing outward. That pressure is sustained by fusion in the core, where lighter elements are transformed into heavier ones, and a portion of mass is released as energy. So long as this trade continues, the star remains in something like equilibrium. It is not peace exactly, but it is a successful stalemate. The trouble with stalemates is that they depend on resources, and stars, however enormous and brilliant, are not exempt from running out of things. They begin with hydrogen in the core, and for a very long time that is enough. In stars like the Sun, this long middle age is practically the whole main story. But in more massive stars, the pace is quicker, and the ending much less gentle. Gravity presses harder because there is more mass. The core gets hotter. Fusion can proceed through heavier and heavier stages. Hydrogen gives way to helium, helium to carbon, and onward through a sequence of more demanding fuels. Each stage tends to be shorter than the one before, which gives the whole late life of a massive star a faintly alarming quality, as though the clock has begun to run faster while the stakes are rising. This is where the long fall toward a neutron star really begins, though at first it does not look like a fall at all. It looks like a star doing what stars do, burning one fuel after another, maintaining itself by ever more strenuous internal means. But there is a trap hidden in the sequence. Fusion is only useful as long as it can release energy overall. For lighter nuclei, bringing them together can free energy and help support the core. For very heavy nuclei, that ceases to be true. There comes a point where fusing further does not provide the pressure support the star needs. Once the core becomes dominated by iron-rich material, the old method of paying gravity off with fusion stops working. The star reaches a kind of bureaucratic nightmare of physics. The bills keep arriving, but the income has ended. Up to this point, matter in the core has remained, broadly speaking, ordinary in the sense that atoms and nuclei still exist in recognizable roles, even if the conditions are already far beyond anything familiar on Earth. The densities are huge, the temperatures ferocious, the pressures staggering. But there are still nuclei, still electrons, still a structure that can be described in the language of atomic and nuclear matter. The long fall becomes much steeper when that description starts to fail. As the iron-rich core grows and pressure support weakens, gravity begins to win more decisively. The core contracts. Contraction raises the temperature, and in some earlier stages that would have helped by igniting another round of fusion. But now the star is nearing the end of those options. Instead of finding a new easy source of support, the core moves deeper into trouble. Electrons become increasingly important because the matter is so compressed that quantum mechanics begins to dominate its behavior. These electrons are fermions, and because fermions cannot all occupy the same quantum state, they create what is called degeneracy pressure. This pressure is not the familiar pressure of hot gas trying to expand. It is a quantum pressure arising from crowding, a refusal written into the rules of matter itself. For a time, that refusal matters a great deal. Degeneracy pressure can support compact objects, as white dwarfs demonstrate beautifully. A white dwarf is the remnant of a lesser star, held up not by active fusion, but by electron degeneracy. It is one of the more elegant outcomes in astrophysics, a dead stellar core supported by pure quantum bookkeeping. But a massive star heading toward neutron star territory is not permitted such an orderly retirement. Its core is too heavy. Gravity presses too hard. Electron degeneracy can delay the reckoning, but it cannot prevent it forever. This part of the story is especially striking because it shows how the universe escalates. First, ordinary thermal pressure is no longer enough. Then quantum pressure from electrons steps in. Then even that becomes insufficient. Matter runs out of gentler ways to resist collapse. It is rather like a building whose lower floors keep giving way one by one, while the upper structure continues pressing down. At some point, the remaining support is no longer asked to cope. It is ordered to do the impossible. As the core contracts further, the electrons are squeezed into states of higher and higher energy. The density rises to truly extraordinary levels. Under these conditions, a new process becomes favourable. Electrons are driven into protons, the two combine, producing neutrons and neutrinos. The neutrinos are ghostly particles that interact only weakly with matter, though weakly in this context still allows them to play an enormous role because the star is so dense and the numbers are so vast. This conversion matters for two reasons. First, it reduces the number of electrons available to provide degeneracy pressure. The star is effectively dismantling one of the last supports holding the core up. Second, it makes the matter increasingly neutron-rich. The long fall from ordinary matter to neutron star matter is no longer theoretical, it is underway. There is something severe about the elegance of this transition. Ordinary matter depends on a beautifully layered structure. Electrons inhabit broad regions around nuclei. Nuclei themselves contain protons and neutrons held together by the strong interaction. Chemistry depends on the electron structure. Solids and liquids and gases all arise from arrangements of atoms and molecules. But when gravity compresses matter enough, those layers stop being independent levels of description. Electrons can no longer remain comfortably separate from nuclei. The architecture collapses inward. Matter loses its familiar spaciousness. The atom, which seems so fundamental in ordinary life, is revealed to be a conditional arrangement rather than an eternal one. This is one of the strange pleasures of extreme astrophysics. It shows that what feels basic to us is often merely local. Atoms are real, yes, but only under circumstances where the universe allows them room. Give gravity enough mass and enough authority, and the atom is no longer the natural unit of structure. It is replaced by denser and more brutal forms of organisation. The collapse of the core is not a leisurely process. Once the conditions pass certain thresholds, the inward plunge can become catastrophic, happening in fractions of a second. The core shrinks with astonishing speed. Densities soar. The matter becomes so compressed that the nuclear scale itself is approached. It is at this point that one can begin to say the core is becoming something like a neutron star, though even that phrase must be handled carefully because the system is in violent transition rather than quiet equilibrium. As the collapse deepens, the character of resistance changes. Electron degeneracy is fading as electrons are captured into neutrons. Neutron-rich matter is appearing. Neutrons, being fermions too, carry their own kind of degeneracy pressure. In addition, nuclear interactions between particles become intensely important at these densities. Matter begins to stiffen dramatically. This stiffening is one of the great turning points in the fall. Gravity has forced the core down through ordinary matter, through electron-supported matter and into neutron-rich dense matter. Now the question becomes whether this new state can halt the collapse. In many cases it can, at least for the central remnant. The collapse does not continue smoothly all the way to oblivion. Instead, when the inner core reaches densities comparable to those of nuclear matter, it becomes much less compressible. The inward rush is checked. The inner region stiffens and can rebound, sending a shock outward into the still falling material above. This is not the whole supernova explanation by itself, because the shock has a difficult life, and neutrinos must assist in reviving it, but it marks the crucial moment where the longfall encounters a new kind of flaw. What is extraordinary is that this flaw is not hard in the ordinary sense. It is not a surface waiting patiently at the bottom of some cosmic shaft. It is an emergent resistance arising from the collective behaviour of dense neutron-rich matter under quantum and nuclear rules. A neutron star is not made by arriving at a solid place. It is made when matter itself becomes so reluctant to further compression that gravity is, for a time, held off. That phrase "for a time" matters. Even when a neutron star is born, the question of its long-term survival depends on mass. There is a narrow balance here, and we are only beginning to see it. If the remnant mass after collapse is low enough, the neutron star can persist. If too much mass remains or falls back inward, the remnant may continue collapsing into a black hole. So the long fall from ordinary matter to neutron stars is not guaranteed to end with a neutron star. It ends, more precisely, with a trial. The newborn compact object must prove that neutron-rich matter can support its weight. Still, to appreciate that later question properly, it helps to stay a little longer with the transformation itself, because it is one of the most radical changes matter undergoes anywhere in the cosmos. Consider what has happened. A star that spent millions of years living through orderly fusion has reached the point where the central core can no longer be sustained by energy generation. Quantum pressure from electrons briefly stands in as a substitute support, but the burden becomes too great. Gravity crushes the core. Electrons are captured into protons. Neutrons flood the matter. The familiar atomic hierarchy dissolves. A compact remnant forms in which city-scale dimensions can contain more mass than a star once did in a volume millions of times larger. This is not just compression, it is a change in ontology. If one can be forgiven a slightly weighty word in a story full of actual weight. Matter is not merely packed closer, it is forced into a regime where the concepts that describe it have changed. The same ingredients are present in some sense, but not in the same social arrangement. Electrons no longer play the roomy chemical role they did in ordinary matter. Nuclei no longer stand apart as tiny islands inside a sea of empty atomic space. The matter has become a dense, degenerate system, dominated by neutrons and their interactions. And yet, remarkably, this descent is part of how the universe renews itself. The collapse of the core does not happen in quiet isolation. It is linked to the supernova explosion that can blast the outer layers of the star into space. Those ejected layers, enriched by the stellar life that preceded collapse and by the violence of the explosion itself, seed the surrounding cosmos with heavy elements. So while the core is falling toward neutron star conditions, the rest of the star may be preparing one of the great acts of cosmic distribution. The same event that destroys the old star may create a compact remnant at the centre and scatter the raw materials of future worlds outward. There is a grim generosity to that. Massive stars do not die tidily. They die in ways that alter their galactic neighbourhoods. A neutron star is therefore not simply a collapsed leftover. It is part of a process that links stellar death to chemical richness. Without such deaths and such remnants, the universe would be poorer in structure and possibility. The long fall from ordinary matter to a neutron star is one of the routes by which the cosmos turns one generation of stars into the ingredients of future planets and life. It is also worth noticing that this fall is long in two senses. It is long historically, because it is prepared over the entire life of the star. The final collapse may be rapid, but the conditions for it are built over millions of years of fusion and structural evolution. And it is long conceptually because it crosses several layers of physical understanding. One begins with ordinary stellar structure and thermal pressure, moves into quantum degeneracy, enters weak interaction processes that convert protons and electrons into neutrons, and arrives at nuclear density matter where the equation of state of dense matter becomes decisive. This is not a single physical idea stretched to an extreme. It is a relay race among different regimes of law. That is one reason neutron stars are so fascinating to physicists. They are crossroads objects. To understand them, one must know something about stellar evolution, nuclear physics, particle processes, quantum statistics, relativity, and hydrodynamic collapse. Few objects demand such a broad coalition of ideas. A neutron star is the product of many kinds of physics arriving at the same emergency. And perhaps that is the most vivid way to imagine the long fall, not as a smooth sinking through one medium, but as an escalating emergency in which one layer of support after another is exhausted, replaced, and then overwhelmed. Thermal pressure has its turn. Electron degeneracy has its turn. Weak interactions begin to change the composition. Neutron-rich matter emerges. Nuclear stiffness rises. Gravity keeps pressing. The core either finds a new temporary stability or continues downward. Each stage is more extreme than the last, and each stage strips away another piece of the ordinary world. By the time the remnant settles into what we can call a neutron star, the fall has transformed almost every meaningful aspect of the original matter. The density is extraordinary. The magnetic fields in some cases are immense. The spin can be astonishingly rapid because the collapsing core conserves angular momentum and thus rotates faster as it shrinks, much as a skater spins faster when drawing in the arms, only with vastly more consequences and considerably fewer applause cues. The object that remains is compact, hot, dense, and governed by rules alien to daily life, and still it is not invincible. The long fall from ordinary matter to neutron stars ends not in security, but in a precarious balance. The remnant has avoided complete collapse for now, but only within a narrow window. This is why the next part of the story matters so much. Once matter has become neutron star matter, what is it actually like inside? What does it mean for atoms to have given up? How do neutrons arrange themselves under such pressure? And what sort of support is really holding the star up? Because to understand how many neutrons reality can tolerate before everything gives way again, we now have to go inward, past the surface appearances into the star itself, where ordinary matter has surrendered and something far stranger has taken its place. By the time matter has fallen all the way into a neutron star, the familiar world has not merely been compressed, it has been overruled. That is the first thing worth holding on to, because our instincts are built out of ordinary matter. We know wood and water and stone and air. We know metals, salts, bones, skin, clouds, books, bread, wires, and dust. Even when we imagine something denser than usual, perhaps a block of lead or the deep interior of a planet, we are still imagining atoms as atoms, still picturing little nuclei with electrons in broad surrounding regions, still relying on chemistry and ordinary electromagnetic structure to explain what the material is doing. A neutron star is not like that. It is not simply a heavier metal, not a super hard rock, not a planet turned up much too far. It is matter in a state where the ordinary atomic arrangement has given up completely. That phrase can sound dramatic, but it is meant quite literally. In the world we know, atoms keep their dignity. Electrons remain associated with nuclei. They may be shared in bonds, shifted in chemical reactions, excited by heat or light, but they still belong to a universe in which atoms are meaningful units. Even in a hot gas, even in a plasma where electrons and nuclei are no longer paired in neat neutral atoms, the ingredients remain recognizable. In a neutron star deeper inside, that whole architecture stops being the right description. Matter has been pushed beyond the point where empty atomic space can exist. The electrons are no longer playing the familiar role of orbital tenants. The nuclei are no longer tidy islands sitting apart from one another. The pressure has forced matter into a regime where density, quantum crowding, and nuclear interaction become the central facts of existence. It is helpful to approach this slowly, layer by layer, because a neutron star is not uniform from the outside in. The surface itself is already peculiar. One can speak of a crust, though this should not invite thoughts of bread or burnt edges or anything comforting from the kitchen. The outermost material is still, in a limited sense, a kind of nuclear solid. There are nuclei packed in a lattice, with electrons moving among them in a highly compressed degenerate sea. This is about as close as the neutron star comes to anything that still resembles matter from the less catastrophic parts of the universe. But even here, the pressure and density are extraordinary by any standard that makes sense to human beings. One is not dealing with a denser version of earthly solid matter. One is dealing with nuclei forced into arrangements by enormous gravity and supported by quantum behavior on a scale that makes ordinary metallurgy look like polite tabletop manners. As one moves deeper, the nuclei become more and more neutron-rich. The pressure is so intense that electrons are driven into higher energy states, and the balance of what counts as stable nuclear composition changes. Ordinary nuclei, the sort found comfortably in laboratories and in the matter around us, are no longer favoured. The environment rewards neutron richness because the system is trying to lower its total energy under impossible compression. Matter is, in effect, redesigning itself to survive the pressure. Then there comes a region where even separate neutron-rich nuclei become difficult to sustain. Neutrons begin to leak out of nuclei into a surrounding sea. This is sometimes described as neutron drip, which sounds far too gentle for what is really happening. It evokes a leaky pipe in a quiet basement rather than one of the more severe reorganizations in nature. But the phrase captures something real. The nuclei can no longer hold on to all their neutrons, because the environment has changed the energetic rules. The star is now entering a state where there are both nuclei and free neutrons in dense coexistence. Atomic identity is already in tatters. Matter is now a lattice of extremely neutron-rich nuclear structures immersed in a degenerate ocean of electrons and wandering neutrons. Even this is not the end of the strangeness. Press deeper still, and the distinction between nuclei and neutron fluid becomes increasingly unstable. At very high densities in the inner crust, matter is thought to adopt bizarre geometries because of the competition between nuclear attraction and electric repulsion. The structures may become layered, rod-like, slab-like, and stranger still, earning nicknames from pasta because physicists, when confronted with the most violent and unnatural forms of matter in the cosmos, occasionally respond by naming them after dinner. It is one of the more reassuring habits in science. Somewhere between complete existential seriousness and cheerful absurdity lies the decision to compare ultra-dense nuclear arrangements to shapes resembling spaghetti and lasagna. These odd forms are not jokes, though the names are. They represent matter trying to minimize energy under crushing pressure, while different forces compete over short distances. The strong nuclear interaction wants nucleons near one another. Electric effects still matter for the protons that remain. The result can be structures unlike anything found under ordinary conditions. This is one of the reasons a neutron star is so scientifically valuable. It contains states of matter that cannot be reproduced in stable large-scale form on Earth. It is less a star in the traditional sense than a natural laboratory built by stellar collapse and run with an alarming disregard for conventional material science. Below these layers one reaches the core proper, and this is where the phrase atoms give up becomes fully earned. In the core, matter is no longer best described as nuclei sitting in a background of electrons. It is a dense fluid dominated by neutrons, along with a smaller fraction of protons and electrons, and perhaps other particles depending on the density. The neutrons are packed so closely that their quantum nature rules the collective behaviour of the star. This is neutron-rich matter in the strong sense, not a collection of ordinary nuclei, not chemistry, not crystal structure in the familiar way, but a degenerate quantum fluid under colossal gravity. At this point, it is worth pausing to notice what has happened philosophically, or at least descriptively. We started with the atom as our unit of matter. Inside the neutron star core, that unit has dissolved. Matter has become something more collective, less separable. You do not have individual atoms behaving politely and only occasionally bumping shoulders. You have a dense sea of particles whose states are constrained by quantum statistics and whose interactions are profoundly shaped by the environment. The matter is not just compressed, it is de-individualized in a sense. The categories that make ordinary matter legible have given way to deeper ones. This is where neutron degeneracy pressure becomes central. Neutrons are fermions, and identical fermions cannot all occupy the same quantum state. In the neutron star core, the available low-energy states fill up. Additional neutrons must occupy higher momentum states. That creates pressure, not from thermal agitation in the everyday sense, but from quantum exclusion. It is one of the strangest and most beautiful mechanisms in physics. A whole star can be supported because particles obey a prohibition. Matter resists collapse because the rules do not allow unlimited crowding without energetic cost. But neutron degeneracy is not acting alone. Nuclear interactions matter too, and this is a detail that becomes increasingly important as one thinks carefully about what is holding the star up. Neutrons do not merely sit side by side refusing to share states. They also interact through the residual strong force. At sufficiently high densities, those interactions contribute significantly to the stiffness of the matter, meaning how strongly pressure rises when the material is compressed further. The exact behaviour of this dense matter, what physicists call its equation of state, is one of the great open questions in neutron star physics. Different assumptions about how the matter behaves at high density lead to different predictions for neutron star sizes, masses, and responses to deformation. So even at the level of a broad description, the inside of a neutron star is not simply a bag of neutrons. That phrase is too crude to be useful, rather like describing a cathedral as a pile of stone, or a symphony as air wobbling about. Not wrong exactly, but inadequate in all the interesting ways. The core is a strongly interacting quantum many-body system under relativistic gravity. It contains mostly neutrons, yes, but that is just the beginning of the story. There is another layer of peculiarity here involving temperature. Neutron stars are born very hot in human terms, unimaginably hot by ordinary experience. Yet compared with the energies associated with the densely packed matter inside them, they can behave as relatively cold degenerate systems. That sounds contradictory only because our words for hot and cold are tuned to kitchens and weather rather than collapsed stellar remnants. In the physics of neutron stars, temperature is not always the dominant player. Degeneracy and density are. The particles are so tightly constrained by quantum conditions that thermal effects, while still important for cooling and evolution, do not define the structure in the same way they would in an ordinary gas. Then there is the possibility that the matter does not remain in the same phase throughout the deepest core. This is where our certainty grows more tentative, and honesty requires that we treat the details with care. At sufficiently high densities, additional particles may appear. Some models allow hyperons, which are heavier relatives of protons and neutrons containing strange quarks. Others suggest that meson condensates could form. Still others consider the possibility that matter dissolves into deconfined quarks, meaning that neutrons and protons cease to be the most useful units, and the core enters a quark matter phase. These are not casual embellishments. They are serious possibilities under conditions so extreme that laboratory intuition offers little guidance. What matters for our present purpose is not choosing a winner among all such models, but understanding what their very existence tells us. It tells us that inside a neutron star, matter is near the edge of known behaviour. The star is not simply dense enough to break atoms, it is dense enough to raise the question of whether neutrons themselves remain the final meaningful structure in the deepest regions. That is a remarkable escalation. We began with atoms losing their individuality, then nuclei lose their independence, then neutrons dominate, then perhaps even neutrons are not final. Matter keeps shedding levels of description under pressure, each one revealing a deeper layer of what it can be forced to become. And all the while, gravity keeps pressing inward. This is what makes the neutron star interior so conceptually powerful. It is not just exotic because it is dense. It is exotic because it reveals how conditional our ordinary categories are. The atom, which feels basic to chemistry and daily life, turns out to be a luxury arrangement that requires enough room. Nuclei, which seem fundamental in schoolbook physics, turn out to be only one stage. Neutrons, so important to the story, may themselves be part of a transitional description. Under sufficient compression, matter strips off one familiar layer after another until the terms of the discussion are no longer the ones we learned first. There is also an extraordinary mismatch between size and content in a neutron star that helps the imagination if one lets it. A neutron star can be only around the size of a city, and yet contain more mass than the Sun. That compression is difficult to grasp, not because the numbers are inaccessible, but because every physical analogy from ordinary life breaks down. We know what cities are like. We know what stars are like from afar, at least visually. Combining the mass of a star with the size of a city feels like a category error, and in some sense it is. Neutron stars are not natural extensions of ordinary objects. They are the result of matter being driven into a regime that our evolved intuitions never had reason to anticipate. One consequence of this extraordinary compactness is that the surface gravity is immense, and the escape speed is a substantial fraction of the speed of light. Time and space around the star are affected in ways that require relativity to describe properly. Light leaving the surface is gravitationally redshifted. Matter falling onto the star can release enormous energy. The object is not a quiet, dense lump sitting innocently in the cosmos. It is a relativistic, compact object with an interior defined by quantum pressure and nuclear interaction, and an exterior space-time curved by tremendous gravity. And yet, for all that, neutron stars are still stars in the sense that they are astronomical bodies with histories and personalities. Some rotate rapidly and sweep beams of radiation across space as pulsars, behaving like cosmic lighthouses with the punctuality of machines and the origin stories of disasters. Some possess magnetic fields so strong that they become magnetas, objects whose magnetic tantrums can outshine ordinary stellar outputs in brief bursts. Some sit in binary systems, pulling matter from companions, growing, heating, flaring, perhaps edging closer to the limits of their own stability. The interior physics is not hidden away in isolation. It shapes observable behaviour, timing, cooling, mass limits, and merger dynamics. The cooling itself is another window into the interior. A newborn neutron star sheds heat efficiently through neutrino emission. These elusive particles, which played such a crucial role during collapse, continue to influence the star's early thermal evolution. Over time, as the star cools, different interior properties become important. Superfluidity may emerge among the neutrons in parts of the interior, and superconductivity among protons may occur as well. These are not the polite low-temperature laboratory phases one first imagines, though they are conceptually related in the sense that quantum collective behaviour appears on a large scale. Inside a neutron star, neutrons may flow in a superfluid state, and protons may conduct with zero resistance in superconducting form, all while the whole object remains under crushing gravity. It is difficult to think of a more convincing rebuttal to the idea that physics should keep its subjects in separate boxes. The presence of superfluid and superconducting components is not just decorative complexity. It matters for the star's rotation and magnetic evolution. It may help explain sudden changes in spin seen in pulsars, little jumps known as glitches, where the star abruptly spins slightly faster. A whole collapsed stellar remnant rotating with astonishing regularity can reveal hidden quantum behaviour in its interior through tiny changes in timing. This is one of the most delightful features of neutron stars. They make the deep interior legible through astronomical observation. The star is not transparent, but it is not mute. All of this returns us to the phrase where atoms give up. It is tempting to treat that as a simple threshold, as though there were one exact moment when atomic dignity resigns and everything afterward is merely neutron business. The reality is more layered. The surrender happens in stages. In the outer crust, nuclei survive under conditions already beyond ordinary imagination. Deeper down, they become stranger and more neutron-rich. Then neutrons begin to escape their nuclear imprisonment. Then bizarre collective structures appear. Then the core becomes a dense fluid where separate atoms no longer mean anything at all. It is less like a switch being flipped and more like a civilization losing one institution after another until a new order takes over. And perhaps that is the right tone to keep here. Neutron stars are not simply dense balls of dead matter. They are places where matter has had every ordinary convenience removed. There is no chemistry in the usual sense, no molecular architecture, no atomic spaciousness, no room for familiar structures, and yet matter does not become featureless. It becomes newly structured at a deeper level. Quantum statistics, nuclear interactions, possible superfluid phases, possible exotic particles, relativistic gravity, all step in where atoms have stepped down. This is why neutron stars occupy such a special place in physics. They are not only remnants of stellar death, they are an answer to a pressure test. How far can matter be pushed before its familiar forms fail? The neutron star says farther than atoms, farther than nuclei as independent islands, farther even perhaps than neutrons in the deepest description. But not infinitely far, there is still a limit. There is still a point beyond which even this astonishing reorganization cannot save the object from continued collapse. Before we get there, though, it is worth savouring just how narrow and extraordinary the achievement already is. A neutron star exists because matter found a way to remain something, rather than become nothing visible to the outside world. Gravity crushed, atoms surrendered, quantum mechanics and nuclear physics improvised a defence. The result was a compact object of immense density, whose interior is one of the strangest places in the known universe. Not because the laws failed, but because they continued with absolute consistency into a regime our ordinary language barely knows how to follow, and that leaves the next question waiting rather sternly at the edge of the room. If this is what matter becomes when atoms give up, and if this quantum nuclear resistance is what holds the star up, then how much of it can reality actually hold? How much neutron-rich matter can exist in this form before gravity ceases to negotiate and decides, once again, to continue the fall? By the time we ask how much neutron matter reality can actually hold, we have already left the comfortable part of physics far behind. We're no longer discussing atoms, chemistry, crystals, or even ordinary nuclear structure in the modest sense taught at the beginning of school science. We're talking about matter that exists only because gravity has forced it into one of the most extreme compromises in the universe. A neutron star is not a natural object in the sense that a stone or cloud is natural. It is a negotiated exception. Gravity has compressed a dead stellar core until atoms have surrendered, electrons have largely lost their old role, and neutrons dominate the interior. Then quantum mechanics and nuclear interactions push back hard enough to stop complete collapse, at least for a while, at least if the mass is not too large. So the question now is not whether neutron matter is strange. That has already been settled beyond appeal. The question is whether this strange state has a limit, and if it does, what kind of limit it is. The short answer is yes, very much so. A neutron star cannot be arbitrarily massive and still remain a neutron star. There is only so much weight that neutron-rich matter can support. Beyond that, gravity wins the argument. But the deeper answer is far more interesting, because the limit is not just a number waiting politely in a box. It depends on how neutron star matter behaves under pressure, how stiff or soft it is, what particles exist in the deepest core, and how strongly pressure rises as density increases. In other words, the maximum mass of a neutron star is not a trivial bookkeeping result. It is one of the clearest windows we have into the nature of matter under conditions that no laboratory can maintain in bulk. To understand why there must be a limit at all, it helps to return to the idea of support. A neutron star is supported primarily by neutron degeneracy pressure, and by the contribution of strong nuclear interactions. Neutron degeneracy pressure comes from the exclusion principle. Identical fermions cannot all occupy the same quantum state, so as neutrons are packed closer and closer together, more and more of them must occupy higher momentum states. This creates a pressure that resists further compression. On top of that, the residual strong interaction among particles contributes to the star's internal resistance. Under the right conditions, these effects together can balance gravity and hold the star up. But balancing gravity is not the same as defeating it permanently. Gravity grows stronger as more mass is added, and in a neutron star, the added mass does not simply sit passively on top like an extra blanket on a bed. It increases the overall gravitational pull inward throughout the object. It also compresses the core further, driving the matter to higher densities where its behavior may change. A heavier neutron star is not just a scaled-up version of a lighter one. It is a more severely compressed object with a deeper interior living under harsher conditions. This matters because pressure support does not increase without limit in a carefree way. For matter to hold up more mass, the pressure must rise appropriately with density. If the matter is sufficiently stiff, meaning pressure grows strongly as density rises, then the star can support more mass. If the matter is softer, meaning it compresses more easily, and pressure does not keep pace as effectively, then the maximum mass is lower. So when physicists talk about the equation of state of neutron star matter, they are talking about the deep relationship between pressure, density, and composition that determines whether the star can survive or not. There is something slightly cruel in the elegance of this. The very existence of neutron stars depends on the same kind of question a civil engineer might ask about an arch or a bridge. How much load can the structure bear before it fails? But here the structure is not steel and concrete. It is dense quantum matter, and the load is gravity strong enough to bend space-time significantly. The same conceptual question remains, but the scale is so wildly enlarged that the comparison becomes almost comical. Still, it is useful. A neutron star is a load-bearing object. Its material is astonishing, but it is not magical. There is a breaking point. That breaking point is often associated with what is known as the maximum neutron star mass. The precise value is still an active area of research because it depends on the equation of state, and the equation of state depends on the detailed physics of dense matter, which remains uncertain in its deepest regimes. Observations of heavy neutron stars have already taught us something important. If neutron stars can be observed with masses around 2 times that of the Sun, then the equation of state cannot be too soft. Matter must be able to support at least that much. That immediately rules out some theoretical possibilities. Reality is doing us a favour, if favour is the word, by building these objects and letting us weigh them from afar. This is one of the most satisfying aspects of astrophysics. The universe performs experiments no laboratory can arrange, then leaves the results scattered across the sky for us to interpret. A neutron star of a certain mass is not merely an object, it is evidence. It tells us that matter at those densities can hold. If we ever establish with confidence that no neutron stars exist above some mass and that heavier remnants become black holes, then that too is evidence. The sky becomes a report from conditions we cannot reproduce directly. Now, one might reasonably wonder why there is any maximum at all if degeneracy pressure becomes stronger as particles are squeezed closer. Should not the resistance simply keep growing and continue to match gravity no matter what? This is where the story becomes a little more subtle. As the densities become extreme, the particles become more relativistic in their motion, meaning their behaviour is increasingly governed by relativity rather than the slower, more familiar regime. The relationship between pressure and density changes. In some circumstances, adding more compression does not give pressure enough extra leverage to keep pace with the growing gravity. There is a deep tension here between how fast gravity intensifies and how effectively matter can stiffen in response. And gravity in general relativity is not merely the old Newtonian pull with a more elegant coat on. In the relativistic description relevant for neutron stars, pressure itself contributes to the gravitational field. That is one of the most unsettling facts in compact object physics. The very pressure supporting the star also adds to the star's effective gravity. It is as though your defenders were also strengthening the opposing army while holding the line. That does not make support impossible, clearly, because neutron stars exist. But it does mean that the contest becomes increasingly difficult, as the object grows more massive and compact. There is therefore no infinite ladder of stable neutron stars of higher and higher mass. Instead, there is a range. Below some lower threshold, depending on formation history, the remnant may not form a neutron star in the first place in the way we are discussing. Above a certain upper threshold, neutron star matter cannot support the mass. In between lies the window of stability. That window is one of the most important narrow corridors in astrophysics, because so much else depends on where its upper end falls. It is also worth noticing that the maximum mass is not only about total mass in the simple sense. Rotation can matter. A rapidly spinning neutron star can support slightly more mass than a non-rotating one because rotation provides additional support against collapse. The star is not simply being held up by internal pressure, but is also helped by centrifugal effects from spinning. This means that the exact collapse threshold can depend on whether the star is spinning slowly or rapidly, and on how that spin evolves with time. A newly formed remnant from a merger might briefly survive as an overmassive neutron star because rapid rotation is helping it. As it loses angular momentum, the extra support fades and collapse may follow later. The object can be living on borrowed time, supported not by matter alone but by motion. That introduces a pleasing complication, because it means the question of how much neutron materiality can hold is not always a static one. Sometimes the answer is this much under slow rotation, a bit more under rapid rotation, perhaps briefly more still under differential rotation, where different parts of the star spin at different rates. Nature, never content with one variable where several will do, allows the threshold to depend on structure, composition and motion all at once. The broad truth remains though, there is no unlimited support. The star can only bargain with gravity for so long, and then there is composition. This is where the uncertainties in the deepest core become especially important. If additional particles appear at high density, such as hyperons or deconfined quark matter, they can soften the equation of state in some models, making the matter easier to compress and reducing the maximum mass. But this is not automatic in every scenario. Some exotic phases may behave differently depending on the details of interaction. The point is that what happens in the innermost core is not an obscure detail tucked away from observation. It influences the largest stable mass, and therefore whether a given remnant survives as a neutron star or collapses into a black hole. There is a charming mismatch here between what is being inferred and how it is being inferred. By measuring radio pulses, X-ray emission, orbital motion, or gravitational waves from catastrophically distant objects, we're trying to learn whether the centre of a compact star contains strange particles or an altered phase of quark matter. That is not a modest ambition. It is the sort of thing that makes human curiosity look slightly unreasonable in the best possible way. But neutron stars invite exactly that. They turn their gross properties, mass, radius, spin, deformability, into clues about microscopic physics. The radius matters too, not just the mass. For a given mass, a larger radius generally suggests stiffer matter, while a smaller radius suggests softer matter. If matter is stiff, it resists compression more strongly, and the star can be larger. If soft, the star is more compact. This is why measuring neutron star radii is so valuable and so difficult. We're not just collecting stellar trivia. We're trying to read the pressure curve of matter at densities where atomic language has already surrendered. A few kilometers more or less in the radius of an object dozens of thousands of light years away can tell us something profound about the behavior of nuclear matter. Gravitational wave astronomy has added an entirely new way of asking the question. When two neutron stars spiral toward each other and merge, they do not behave as simple, rigid points. They distort in each other's gravity. The ease or difficulty of that distortion depends on how their matter responds to tidal forces, which in turn depends on the equation of state. So by listening to the gravitational wave signal from inspiraling neutron stars, one can infer something about how squishy or stiff they are. It is difficult not to admire the sheer indirectness of this. Two dead stars crash together in a galaxy far away. Space-time ripples across the universe, and from those ripples we attempt to deduce how much neutron matter reality can tolerate before collapse. This also highlights a profound fact. The maximum mass of a neutron star is not merely a sterile limit, it governs outcomes. In a core collapse supernova, the remnant mass determines whether a neutron star survives. In a neutron star merger, the combined mass and the equation of state determine whether the aftermath is a more massive neutron star for a while. Perhaps a hypermassive remnant supported by rotation and thermal effects, or an immediate black hole. The threshold shapes the light, the neutrinos, the gravitational wave signal, the amount of matter ejected, and the synthesis of heavy elements. The limit is not hidden in a textbook corner. It is active in the universe. There is a further subtlety that makes the whole question even more interesting. The maximum mass is not only about where a neutron star stops being stable in practice. It is also bound by a deeper principle from relativity, namely that the equation of state cannot imply signals travelling faster than light through the matter. That places an upper bound on how stiff matter can be, so there is an interplay between support and causality. Matter cannot simply become arbitrarily incompressible to rescue the star, because the laws of relativity place constraints on how pressure can respond. Reality offers support, but not cheats. That seems fitting somehow. Neutron stars exist because quantum mechanics and nuclear physics offer a legitimate resistance to gravity. Black holes exist because that resistance is not unlimited. The universe does not rescue massive stellar remnants with loopholes. It permits only what the laws coherently allow. Somewhere in that constraint lies a form of beauty, though perhaps a stern one. One can imagine the interior of an increasingly massive neutron star as a place where every additional bit of mass raises the stakes everywhere below it. The core is compressed more tightly, the density climbs. Whatever phases of matter are possible are pushed closer to their limits. The star becomes more compact, space-time around it more strongly curved, the whole structure more precarious. There is no comfortable heaviness here. A more massive neutron star is not merely a larger neutron star, it is a more endangered one, and perhaps that is the right emotional tone for these objects. They are survivors, but only narrowly. A neutron star represents one of the last successful forms matter can take before gravity stops negotiating. It has already endured the death of a massive star. It already exists in a regime where atoms are gone, ordinary nuclei are no longer the main story, and dense neutron-rich matter is under immense pressure. To ask how much more it can hold is to ask how close it lives to catastrophe by its very nature. The answer, in broad terms, is not much more than a few solar masses, and in practice the stable range is narrower still. That may sound almost disappointing after all this build-up. Surely something so dramatic should be allowed a more extravagant number. But that modest upper limit is exactly the point. It reveals how narrow the neutron star window really is. Too small a remnant and you do not get a neutron star in the relevant way. Too large a remnant and you do not keep one. The allowable range is enough to matter enormously and small enough to be scientifically precious. This narrowness has consequences that ripple outward through cosmic history. If neutron stars could support much more mass, then fewer collapsing stellar cores would become black holes. The population of remnants would change, merger outcomes would change, the production of heavy elements in mergers and supernova-related events might change as well. If neutron stars could support much less mass, then many objects that now survive briefly or permanently as neutron stars would vanish into black holes instead. The universe would lose one of its key intermediate outcomes. The fact that neutron stars exist in the range they do is part of why the universe is chemically and dynamically the way it is. There is also a delightful logical structure to the whole problem. We began by asking how many neutrons can be stacked before reality breaks. At first that sounded like a whimsical exaggeration. By now it turns out to have been almost too accurate. Reality permits neutron matter only when enough mass is present for gravity to force the issue, and only up to the point where gravity once again overcomes the resulting support. The existence of neutron stars is therefore bracketed on both sides by refusal. Too little and neutron matter does not self-assemble. Too much, and it cannot remain stable. The amount that reality can hold is not arbitrary accumulation, but a narrow tolerated interval. That means the neutron star itself is less like a final destination, and more like a pause point. It is the place where matter, under the most crushing conditions short of total collapse, manages to erect one last successful form of resistance. It is the universe saying this much can still stand, but only this much. Beyond it lies the next threshold, and the next threshold is not another kind of star in the ordinary sense. It is the point where the remnant no longer has a stable material identity available to it as an object supported by internal pressure. It becomes a black hole. So when we ask how much neutron matter reality can actually hold, the answer is as much as can be supported by neutron degeneracy, nuclear interactions, relativistic structure, and perhaps rotation, within the constraints imposed by causality and the true equation of state of dense matter. That is the formal version. The more human version is that reality can hold an astonishing amount, but only just. Enough to create stars made of crushed neutrons, enough to let them exist as distinct objects, enough to make pulsars and mergers and all the strange astrophysical consequences that follow, but not enough to let them grow without bound. And that brings us naturally to the next step, because once one sees that neutron stars are living within a narrow margin, the obvious question is what the final tipping point looks like. How does the star lose? How does an object already so dense, already so extreme, already so victorious over one stage of collapse, finally cross the line where a neutron star becomes a black hole? A neutron star lives on the edge of a refusal. That is perhaps the clearest way to understand the tipping point where it becomes a black hole. For all its density, all its gravity, all its violence of origin, a neutron star is still a successful act of resistance. It is matter saying not yet to total collapse, not yet to the disappearance of any stable material surface, not yet to the point where even dense neutron-rich matter can no longer hold shape against the inward demand of gravity. A black hole begins where that refusal fails. This is what makes the transition so profound. We're not talking about a normal star aging into a slightly more dramatic version of itself. We're talking about one of the most compact and extreme stable objects in the universe, crossing over into something that is no longer held up by matter in any ordinary sense at all. The neutron star is already a remnant of catastrophe, already a body in which atoms have given up, nuclei have surrendered their independence, and quantum mechanics plus nuclear interaction are doing everything they can to hold off further disaster. So when that object itself can no longer remain stable, there is no gentler backup plan waiting behind it. There is no denser, ordinary star form with a bit more patience and a stronger constitution. There is collapse, and then there is black hole. To appreciate the tipping point properly, it helps to remember what is doing the holding up in the first place. A neutron star is supported by pressure that comes from the exclusion principle acting on neutrons, from the strong interactions among particles in dense matter, and in some cases by rotation, if the star is spinning fast enough to help support itself against gravity. These are real and formidable forms of resistance. They are the reason neutron stars can exist at all. But none of them are infinite. They all work within limits. Gravity, meanwhile, becomes more severe as more mass is added and as the star becomes more compact. Eventually the star enters a regime where every increase in mass pushes it close to the point where no stable configuration remains. That last phrase matters. No stable configuration remains. A neutron star does not become a black hole because it somehow gets tired, or because one dramatic event flips a magical cosmic switch labelled doom. It becomes a black hole when the laws of physics no longer allow a stable neutron star solution for that mass, structure, rotation, and internal composition. In other words, the tipping point is not a visual threshold in the everyday sense. It is a structural one. The star reaches a point where there is simply no way for matter to arrange itself and still support the object against its own gravity. This is one reason the transition can be difficult to imagine. In ordinary life, most failures are local before they are total. A bridge develops cracks. A building sags. A tree leans. There are signs, deformations, compromises. A neutron star near its upper mass limit is certainly more compressed and more precarious than a lighter one, but once it crosses the true threshold, there is no new equilibrium waiting. The failure is global. The entire object has run out of permissible support. One route to that threshold begins at birth. When a massive star collapses in a core collapse supernova, the remnant core may initially form a neutron star. But if the mass of that remnant is too great, or if additional material from the exploded star falls back inward afterward, the newborn neutron star may not survive for long. It can be born already over the line, or close enough that continued accretion pushes it across. In that case, the neutron star is less a final outcome than a brief way station. For a short time it exists as a compact remnant supported by dense matter, and then the support fails. Collapse resumes, a black hole forms. Another route is slower and in some ways even more unsettling. A neutron star in a binary system can draw matter from a companion star over time. This process can spin it up and increase its mass. Such stars may appear as pulsars with astonishing regularity, quietly gaining material year after year, century after century, perhaps for vast stretches of time. But if enough mass accumulates, the star is being nudged toward its own structural limit. It is rather like watching someone steadily pile weight onto a shelf built from the most extraordinary material in the universe. For a long while it holds. Then one day, the shelf is no longer a shelf. It has become a lesson. There is also the dramatic case of neutron-star mergers. Two neutron stars orbit one another, radiating energy away in gravitational waves, spiraling inward over millions or billions of years until the final dance becomes rapid and violent. They collide. In the aftermath, the combined remnant may form a more massive neutron star for a brief time, especially if rapid rotation helps support it. But often that support is temporary. As the remnant sheds energy and angular momentum, as rotation slows or internal differentials settle out, the extra support fades. The star, once held up partly by motion, can no longer sustain itself. Collapse follows. A black hole emerges from the wreckage. This is one of the reasons neutron star mergers are so rich scientifically. The exact timing of collapse, immediate or delayed, affects what electromagnetic signals are produced, how much matter is ejected, how heavy elements form, and what the gravitational wave signature looks like. The tipping point is not merely a hidden internal fact. It changes what the universe visibly does. Now, what does the tipping point feel like from the inside? If one were somehow to ask a question that matter cannot answer, it would not feel like crossing a line painted on space-time. The star would simply find that its pressure no longer rises quickly enough, that compression accelerates rather than settles, that the central density increases without reaching a new stable plateau. Once that process starts in earnest, collapse can become unstoppable. The core contracts further. Gravity strengthens as the radius shrinks. Space-time curvature grows more severe, and because the object is already relativistically compact, the descent from neutron star to black hole is not a leisurely continuation of an ordinary process. It is the loss of the last material defense. One should be careful, though, not to imagine the star being crushed by some outside hand. Gravity and general relativity is not a force reaching in from elsewhere. It is the geometry of space-time responding to mass and energy. The neutron star becomes a black hole when its own structure can no longer maintain itself against that geometry. The star is not being attacked from outside. It is succumbing to the consequences of its own mass concentrated within too small a volume. There is something starkly elegant in that. A black hole is not an object added on top of matter by some extra ingredient. It is what can happen when matter fails to remain matter in the form needed to support itself. One can think of the neutron star as the final successful matter configuration, before gravity stops allowing such success. After that, what remains is no longer a star supported by pressure. The details of the internal matter become hidden behind the horizon in any observational sense that concerns the outside universe. The event horizon itself deserves a moment of calm description, because it is often wrapped in unnecessary melodrama. The event horizon is not a solid surface, and not a cosmic cliff edge with dramatic music attached. It is a boundary in space-time beyond which events cannot send signals back out to distant observers. Once collapse proceeds far enough that such a boundary forms, the object has become a black hole in the meaningful astrophysical sense. What happens inside thereafter is no longer available to the rest of the universe in the usual way. The star has passed from being an exposed material structure to being a region defined by causal separation. That causal separation is one of the reasons the transition feels so philosophically final. A neutron star can still be studied as matter. It has a surface, an exterior field, a radius, a composition we try to infer, cooling behaviour, oscillations, crustal events, magnetic drama. A black hole, by contrast, is much more austere in what it presents externally. Mass, spin, charge if relevant, though for astrophysical black holes charge is generally negligible. The rich microscopic details that mattered so much for determining whether the star would survive no longer appear in the same way to the outside world once the horizon forms. The object has crossed from complexity that can be probed to simplicity imposed by relativity, and yet the irony is that all the rich internal physics still mattered tremendously in determining when collapse happened. The equation of state of dense matter, the role of possible exotic particles, the contribution of rotation, the thermal state of the remnant, the transport of angular momentum, all of these influence whether the neutron star survives and for how long. The black hole may appear externally simple once formed, but the route to it runs through some of the most complicated matter physics in the universe. This is part of what makes the tipping point so scientifically precious. If one can constrain the maximum neutron star mass observationally, then one has learned something profound about dense matter. If one observes a merger remnant collapsing after a delay of a certain kind, one gains clues about how much support rotation was providing and what the matter was like. If a compact object is measured to have a mass too high for any plausible neutron star, then the universe is telling us the threshold has been crossed. The line between neutron stars and black holes is therefore not merely a category boundary, it is an empirical probe of fundamental physics. There is also a certain severity in how narrow this line is. One might imagine that there should be a broad transition region with many intermediary stable objects, a leisurely spectrum of ever denser stars gradually changing character. Reality is less generous. There may be nuances and temporary states, yes, but the stable, long-lived categories are limited. White dwarfs are held up by electron degeneracy, neutron stars by neutron-rich matter and nuclear physics, black holes by no material pressure support at all. The steps are not many. Each one marks a failure of the previous support mechanism. The neutron star exists because electron-supported matter could no longer hold. The black hole appears because neutron-supported matter can no longer hold. The whole ladder of compact objects is built from successive admissions that reality has boundaries. The tipping point also reveals something subtle about gravity and scale. For tiny clumps of neutrons, gravity is irrelevant. For neutron stars, gravity is decisive but not yet all-powerful. For black holes, gravity has pushed past the regime where any known matter configuration can remain exposed and stable. The same interaction that was negligible for a single neutron becomes the final arbiter for astronomical collections of them. This scale dependence is one of the marvels of physics. Nothing in a lone neutron suggests a black hole, and yet enough neutrons, enough mass, enough compression, and the geometry of the universe changes its answer completely. A useful way to picture the approach to the limit is to imagine the neutron star becoming increasingly compact for its mass. The deeper core is squeezed harder. If exotic particles appear, they may soften the matter and hasten the crisis. If the star rotates rapidly, that may postpone collapse by providing extra support. But there comes a point where every additional fraction of mass, or every loss of rotational support, moves the star from possible to impossible. At that point, collapse is not one option among many. It is the only option left. And because relativity is involved, there is a strange observer dependence in how one talks about the process. To an observer far away, collapse toward a black hole is described through signals that become ever more red-shifted and delayed. To the matter falling inward, the collapse proceeds through its own proper time. This can make discussions of black hole formation sound paradoxical if handled carelessly. But the essential astrophysical point is simple enough. Once the collapsing remnant becomes compact enough that an event horizon forms, the object is a black hole as far as the external universe is concerned. The neutron star phase is over. What is perhaps most striking is how little extra indulgence gravity allows at the end. A neutron star is already an object that feels impossible by everyday standards. Its density is extreme, its gravity immense, its surface conditions unlike anything familiar, its interior deeply alien. One might think such an object had already exhausted the universe's appetite for extremity. But from gravity's point of view, a neutron star is still only a partial surrender. It is matter still saying, "I remain an object." A black hole begins where even that claim can no longer be sustained in exposed form. This lends the neutron star a kind of tragic dignity. It is not a failed black hole in any simple sense, nor is a black hole merely a neutron star that got carried away. Rather, a neutron star is the last stable negotiation available to matter under crushing gravity. It uses quantum rules and nuclear interactions to hold itself together in defiance of what would otherwise happen. If it crosses the tipping point, that is not because it was never real or never successful. It is because even its extraordinary success had a narrow limit, and that limit matters for everything around it. The threshold determines what remnant stars leave behind. It determines whether a merger ejects matter rich in neutrons for forming heavy elements, or swallows more of it quickly into a black hole. It influences the brightness and duration of transient events, the pattern of gravitational waves, the demographics of compact objects in galaxies, and the balance between one kind of cosmic aftermath and another. The difference between neutron star and black hole is not merely academic classification, it changes what the universe gets to keep. In some sense, the tipping point is where the story of matter turns into the story of space-time. Up to that point, one asks what matter can do, how pressure responds, what particles exist, how quantum mechanics and nuclear physics behave under impossible conditions. Beyond it, the central defining feature becomes the geometry of the collapsed region itself. Matter still exists, of course, in some description, but it is no longer the star we can interrogate from outside. The horizon has taken over the narrative. That is why the transition feels so absolute, even though the physics leading up to it is gradual and detailed. The neutron star may approach the limit by slow accretion, or sudden merger or fallback after supernova. It may hover temporarily above ordinary support thanks to rapid rotation. It may spend time in a metastable state, living on deferred collapse. But once the final line is crossed, the category changes in a way nothing prior quite prepares us for. The object ceases to be a star supported by matter and becomes a black hole characterized by the causal structure of space-time. And this is where our central theme becomes especially clear. How many neutrons can you stack before reality breaks? The answer is not an unlimited accumulation followed by a dramatic crack. The answer is a narrow regime where neutron matter can exist, because gravity has become strong enough to force it, followed by another threshold where gravity becomes too strong for even that. The break is not in the laws remain perfectly intact. What breaks is the possibility of matter maintaining itself as a neutron star. There is, oddly enough, something constructive in that severity. Because the universe does not allow neutron stars to support arbitrary masses, there is a meaningful division between collapse outcomes. Some remnants remain neutron stars, others become black holes. That division helps shape supernova, mergers, element production, and the architecture of cosmic history. If the tipping point lay elsewhere, the later universe would not be the same. The narrowness of the neutron star window is part of why the cosmos produces the mixture of violence and fertility that it does. So the moment where a neutron star becomes a black hole is not just the end of one object. It is the closing of one of the last doors through which matter can remain visibly organized under gravity. Beyond that door, the universe continues, but not with a surface, not with pulsar timing, not with crust and core and dense matter phases we can infer. Beyond that door lies a black hole, and behind that horizon the story changes language entirely, which means that by now we can finally see the larger shape of the problem. Too small a collection of neutrons refuses to become neutron matter. Large enough and gravity forces a star's core into that state, giving us a neutron star. Too large and even neutron matter cannot hold. Between those two refusals lies a very narrow and very important cosmic interval. And that interval is not just a curiosity of compact objects. It is one of the reasons the universe can produce supernovae, heavy elements, planets, and eventually creatures capable of wondering why this balance is so precise in the first place. What makes this whole story so remarkable is not merely that neutron stars exist, or that black holes exist, or even that matter can be pushed from one state into the other by gravity. The truly striking thing is how little room there is between these outcomes. The universe does not allow neutron matter on just any scale, under just any condition, in some broad forgiving category where one can casually drift from one state to another. It allows a very narrow window. Too small a collection of neutrons and there is no stable neutron matter in the strong astrophysical sense we have been building toward. Too much mass, and the neutron star cannot hold itself up. Between those two refusals lies one of the most delicate structural intervals in all of nature. It is worth lingering with that because our instincts generally prefer wide categories. We like to imagine that nature works in generous ranges. Water can be a puddle or a lake or an ocean, and still be recognizably water. Rock can be a pebble or a mountain, and still be rock. Stars themselves come in many sizes and live many sorts of lives. We become used to the idea that the universe is flexible, abundant, spacious in its allowances, and in many ways it is. But every so often one encounters a domain where the permissive broadness gives way to a narrow ledge. Neutron star matter lives on one of those ledges. This is not simply a matter of inconvenient technical details. The narrowness is the point. If pure neutron matter were easy to make and stable on small scales, then the universe would contain all sorts of little neutron objects, and the dramatic formation of neutron stars would lose much of its special status. If neutron-rich, dense matter could support arbitrarily large masses, then many objects that now become black holes would remain neutron stars instead. The whole landscape of stellar death and compact remnants would be different. The universe we know depends not merely on the existence of neutron matter, but on how tightly its existence is constrained. There is something almost architectural about this. Imagine a structure that can only stand if it is built within a very particular range of dimensions. Make it too small and the materials do not lock together. Make it too large and the supports fail. Only within a narrow interval does the thing hold. That would be a peculiar building. One might even hesitate to trust it. Yet that is more or less what the universe has done with neutron stars. It has made a class of objects that exist only because a very specific balance is struck between microscopic law and macroscopic gravity. On the small side of the window, the problem is that neutrons do not simply self-assemble into durable lumps. Free neutrons decay. Tiny neutron clusters are not stable the way ordinary matter is stable. The strong interaction, though powerful, does not provide a universal invitation for pure neutron droplets on modest scales. Gravity is far too weak in such small systems to force the issue. So matter remains in the more familiar arrangements of nuclei, atoms, molecules, solids, liquids, gases, plasma, all the forms that make chemistry and planets and breakfast tables possible. Neutron matter, in the neutron star sense, refuses to appear unless gravity has become overwhelming. On the large side, the refusal changes character. Gravity is no longer too weak. It is too strong. It has become strong enough not only to create neutron-rich matter, but to threaten it. A neutron star can survive only because neutron degeneracy pressure, nuclear interactions, and in some cases rapid rotation, provide enough support to counterbalance gravity. But that support is finite. Add too much mass and the star loses. There is no denser stable matter configuration available, at least none that can remain exposed as a star supported by material pressure. The object collapses into a black hole, so the neutron star is born in the middle of two impossibilities: too little, and it cannot exist; too much, and it cannot remain. That is why the phrase narrow cosmic window is not just convenient wording. It is a faithful description. Neutron stars are not broad middle ground objects. They are special occupants of a small permitted interval, and once one sees that, a deeper realization follows. The narrowness is not an accident sitting off to one side of astrophysics. It helps determine how the universe evolves, because stars do not all die the same way. Their masses differ, their cores reach different conditions, their remnants land in different parts of this permitted window, or miss it entirely. Some stars leave white dwarfs, some leave neutron stars, some leave black holes. The distribution of those outcomes shapes what kinds of explosions occur, how much matter is ejected, what sort of compact remnants populate galaxies, and what signals we later observe as pulsars, X-ray binaries, or gravitational wave events. This means that the neutron star window functions almost like a gatekeeper in cosmic history. It decides, in effect, which collapsing cores get to pause as neutron stars, and which go straight on to black holes. That pause is enormously important. A neutron star is not merely a remnant lying around after the interesting part is over. Its very formation and survival influence the supernova process, the transport of energy by neutrinos, the amount of fallback matter that remains outside the final collapsed object, and the kind of later astrophysical behaviour that becomes possible. There is a common temptation, especially when discussing compact objects, to think only in terms of endpoints: white dwarf, neutron star, black hole, as though these were just labels applied after the real drama is finished. But in truth, the categories themselves help shape the drama. If a collapsing stellar core reaches the neutron star window and survives there, even briefly, the whole event can look different from one in which collapse rushes directly onward to a black hole. The presence of a temporary or long-lived neutron star changes the flow of energy, the behaviour of shock waves, the timing of collapse, and the amount of material that can be expelled rather than swallowed. That matters because expelled material is where so much of cosmic richness comes from. Heavy elements are not made only in the calm interiors of stars. Many of the heaviest are associated with violent neutron-rich environments, including neutron star mergers and possibly certain supernova-related processes. If the compact remnant window were substantially different, the balance of those events would shift. The chemistry of galaxies would shift. The inventory of what later becomes planets, oceans, atmospheres, and biology would shift. One can think of the neutron star window as a kind of cosmic throttle. It controls how often matter is held in a neutron star state versus how often it disappears quickly behind a black hole horizon. And those alternatives are not interchangeable. A neutron star can merge with another neutron star and eject a neutron-rich material into space. A black hole cannot do that in the same way from its own interior, because whatever crosses the horizon is no longer available to the outside universe. A neutron star can radiate, spin, host a crust, support magnetic fields with extraordinary observational consequences. A black hole offers a different kind of aftermath. The universe needs both, but it does not get the same results from each. This is why the narrowness of the window feels less like a curiosity and more like a hinge. It is one of the points where the deep laws of matter meet the large-scale structure of cosmic history. On one side are quarks, neutrons, fermionic exclusion, nuclear interaction, dense matter equations of state. On the other side are exploding stars, merger remnants, heavy element production, planetary composition, and eventually life. The window is where those scales connect. There is something deeply satisfying in that, because it reminds us that the universe is not organised in separate departments that never speak to one another. Particle properties influence stellar remnants. Stellar remnants influence element creation. Element creation influences planets. Planets influence chemistry. Chemistry influences the possibility of life. So when we talk about how much neutron materiality can permit, we're not trapped inside some abstract corner of theoretical physics. We're discussing one of the many ways the large visible universe depends on the exact behaviour of the very small. And exact really is the right word. Change the properties of the neutron a little. Change the details of nuclear interaction. Change the stiffness of dense matter. Change the upper mass limit of neutron stars. The outcome pattern shifts. Perhaps more collapsing cores become black holes. Perhaps fewer neutron stars survive. Perhaps mergers look different. Perhaps the amount of R process element production changes. One need not claim that every tiny change would erase life in some melodramatic instant. The universe is often more adaptable than our first dramatic instincts suggest. But it is fair to say that the neutron star window is one of those places where a different balance would make for a recognisably different cosmos. There is also a more subtle beauty here, namely that the window is narrow because two very different realms of law are both being taken seriously at once. On the one hand, quantum mechanics and nuclear physics govern what dense matter can do. On the other hand, gravity, especially in its relativistic form, governs what mass compressed into a small region does to space-time and to itself. Neutron stars are what happen when those two descriptions manage to coexist in a fragile but real truce. The truce is not generous, because neither side gives way completely. Matter resists. Gravity insists. The result is a limited domain of possible objects. That makes neutron stars feel almost improbable, though of course they are not improbable in the statistical sense. The universe makes them often enough. But they feel conceptually improbable because they require such different pieces of reality to come into balance so narrowly. A white dwarf is already a quantum object on a stellar scale. A neutron star goes further. It is matter compressed to densities where the distinction between particle physics and astrophysics becomes hard to maintain, and it works only in a limited interval. That makes each neutron star less like a routine star and more like a visible statement that the laws have aligned just enough to permit this thing. One should also notice that the narrow window is not just about the stable, long-lived population, it shapes transient states too. In neutron star mergers, the immediate aftermath can be a remnant hovering at or above the ordinary non-rotating maximum mass, temporarily supported by rapid rotation and thermal effects. Such remnants may live briefly before collapsing. Those brief lives matter enormously for what is emitted and ejected. The amount of time the remnant survives can affect the electromagnetic glow, the neutrino environment, the synthesis of heavy nuclei, and the structure of the gravitational wave signal after merger. So even the temporary use of the window has cosmic consequences. That is a wonderfully strange sentence when one pauses over it. Temporary use of the window. It sounds like a bureaucratic permit in a celestial planning office, yet it captures something real. The universe can pass matter through the neutron star state briefly, or keep it there much longer, and the difference changes the visible aftermath. A narrow window, even when occupied for only moments, can shape the future. The lower side of the window deserves one more look as well, because it helps prevent a misconception. The universe is not filled with neutron matter whenever neutrons are present in abundance. Neutrons exist in nuclei all over ordinary matter. They are part of atoms in your body and in the ground and in the stars. But that does not mean neutron matter in the neutron star sense is common. It is not enough to have neutrons. One needs conditions where matter is so compressed that neutron-rich degenerate behavior becomes the relevant collective state. The lower boundary of the window is therefore a reminder that composition alone is not destiny. Environment matters, scale matters, pressure matters, gravity matters. This is one of the recurring lessons of physics, and it deserves repeating because it is so easy to forget. A substance is not only what it is made of, it is also what state it is in, under what conditions, in what collective arrangement, with what forces dominating its behavior. Carbon can be graphite or diamond, water can be vapor or ice. Matter containing neutrons can be ordinary nuclei or neutron star matter, depending on how the universe has arranged the conditions. The lower edge of the neutron star window is the place where that principle becomes especially severe. Without enough gravity, neutron matter is not merely rare, it is disallowed as a stable large-scale state. On the upper side, the lesson is the opposite one. Even the right state of matter is not enough if gravity pushes too far. Neutron-rich dense matter can resist only within limits. This means that the neutron star window is bounded not just by permission, but by exhaustion. Matter has one last extreme way to hold itself up, and then it runs out. Beyond that lies the black hole, not as a dramatic flourish added for effect, but as the result of no stable exposed material configuration remaining. There is a sobering clarity in this. The universe is not endlessly inventive in the face of collapse. It has a few major strategies: thermal pressure during a star's active life, electron degeneracy and white dwarfs, neutron-rich matter in neutron stars. After that, for sufficiently massive remnants, there is no new material strategy available that we observe as a stable star. The narrow window is therefore one of the last places where matter gets to remain visibly structured before space-time takes over the conversation. And because that is true, the window becomes a site of creative tension in the cosmos. It is a limit, yes, but also a productive one. The universe often gets its richest behavior not from unlimited freedom, but from constrained possibilities. Planets exist in habitable zones, stars burn for finite lifetimes, nuclei have stability bands, and neutron stars occupy a narrow mass regime. Constraints generate structure. The neutron star window is one more example of that principle. It is narrow, and because it is narrow, it creates a meaningful distinction in stellar evolution with enormous consequences. One can almost think of it as a selective filter for catastrophic events. Not all stellar deaths produce the same aftermath because not all collapsing cores land in the same region relative to the window. Not all compact object mergers leave the same remnant because the combined mass and rotation do not always fall in the same place relative to the window. The filter sorts outcomes. Some matter remains outside horizons long enough to participate in further visible astrophysical history. Some does not. The difference shapes what the universe gets to keep in circulation. This is particularly important when one thinks ahead to planets and life. Planets are made of heavy elements. Those elements were forged in stars and in violent post-stellar events. If the neutron star window were absent, shifted, or radically widened or narrowed, the relative frequency and character of those element-producing events would change. One must be cautious not to make simplistic Wonka's claims about so vast a network of processes. Life does not depend on a single switch, but it does depend on a long chain of physical conditions producing a chemically rich universe. The neutron star window is part of that chain, and that is perhaps the most profound thing about it. The window exists at an almost absurd remove from human life. It concerns collapsed stellar cores, neutron degeneracy, relativistic structure, and masses comparable to stars compressed into city-sized objects. Nothing about it sounds domestic or relevant to morning routines or forests or coastlines or conversation. Yet through the history of stellar death and elemental creation, it reaches all the way into the ordinary world. The stability of neutron stars and the instability beyond them helps shape the availability of the materials from which ordinary worlds are built. So this narrow interval between too small and too much is not merely a technical threshold in compact object theory. It is one of the channels through which the universe turns violent collapse into future possibility. The fact that matter can be pushed into a neutron star state but only up to a point means that the cosmos has both a pause and a plunge. It can stop collapse temporarily in some cases and let it continue in others. That diversity of outcomes is fertile. It produces variety in remnants, explosions, mergers, and ejected matter. Variety in those processes produces variety in what later condenses into stars and planets. Somewhere downstream of that sits every rocky world. There is also, I think, a quiet, philosophical comfort in realizing that the universe does not make interesting things by avoiding danger. It often makes interesting things by living close to danger. Neutron stars exist close to collapse. Heavy element synthesis often happens in violent environments. Supernovae are not controlled engineering projects. The cosmos is productive not because it never goes near catastrophe, but because it can hover near thresholds where catastrophe and creation are intertwined. The neutron star window is one of the clearest examples. It is a narrow place where matter nearly loses, but not quite. And because it does not quite lose, the rest of the universe gains possibilities. By now, the larger shape of the argument is almost fully visible. Too few neutrons and no stable neutron matter object appears. Enough mass and gravity forces matter into a neutron star. Too much mass, and even that compact resistance fails into black hole formation. Between those two prohibitions lies a small but crucial interval. That interval governs which stellar deaths leave visible dense remnants, and which do not. It helps regulate the balance of neutron star mergers and black hole formation. It influences how heavy elements are produced and dispersed. It is, in that sense, one of the reasons the universe is not merely full of hydrogen and silence. Which brings us naturally to the next step, because once we understand that this narrow balance exists, the real significance of it becomes impossible to ignore. The question is no longer only how the window works, but why its existence matters so much for the larger story of cosmic structure. Why this delicate balance helps make supernovae, heavy elements, planets, and eventually us. By now the question has stopped sounding playful and started sounding foundational, which is usually how the best physics questions behave if you leave them alone long enough. How many neutrons can you stack before reality breaks first looked like a slightly mischievous thought experiment. The kind of thing one asks almost to see whether the universe will roll its eyes and decline to answer. But the deeper we have gone, the clearer it has become that the answer is tied to some of the most important features of the world we actually inhabit. The narrow balance between too little neutron matter and too much is not some obscure technicality sitting in a distant corner of astrophysics. It is one of the reasons the universe can produce spectacular stellar deaths, forge and scatter heavy elements, assemble rocky planets, and eventually make chemistry rich enough for life to emerge. The delicacy of the balance is part of the fertility of the cosmos. That is worth saying plainly because the route from neutron stars to people is not obvious at first glance. A neutron star is a compact remnant left by catastrophic stellar collapse. It is dense, violent in origin, difficult to picture, and in no ordinary sense hospitable. Nothing about it suggests forests, oceans, cells, or afternoon tea. If anything, it seems like precisely the sort of object one might classify under fascinating but not directly relevant to ordinary existence. Yet astrophysics has a habit of humbling that sort of classification. The universe is connected in long chains. What looks remote in scale or mood can still sit upstream of something intimate. A dying star can influence the existence of your bones. A merger of compact remnants can affect the chemistry of a future planet. Neutron-rich matter, for all its severity, is part of the long story of why the universe is not made only of the simplest things. To see why, it helps to begin with supernovae, because they are one of the great turning points in stellar life. A massive star spends much of its existence fusing lighter elements into heavier ones in its core, holding itself up against gravity through the energy released by those reactions. For millions of years this works. The star shines, balances, evolves, and quietly manufactures a layered interior. But that strategy is not endless. Eventually the core reaches a composition, especially iron-rich conditions, where further fusion no longer provides the support needed to keep gravity in check. The core collapses, matter is driven into extreme density, electrons are captured into protons, neutrons flood the core. A neutron star may form if the remnant mass lands within the narrow permitted range, and this is where the delicate balance begins to matter for the outside universe. If the collapsing core can form a neutron star, even briefly, then the collapse does not simply continue inward without interruption. Instead, the stiffening of dense neutron-rich matter provides a kind of resistance. The inner core halts or rebounds, shock waves form, neutrinos pour through the star in colossal numbers. The details are complicated, as one would expect from an event involving the collapse of a stellar core under relativistic gravity, while weak interactions and hydrodynamics compete for relevance. But the broad point is clear enough. The temporary survival of a neutron star or proto-neutron star changes the entire character of the explosion. That change matters because a supernova is not just an ending. It is a dispersal event. The outer layers of the star, enriched by the products of stellar fusion and by explosive processing during the collapse itself, can be hurled into space. Material that once sat buried in the interior of a massive star is now returned to the galaxy. Without that return, the later universe would be a much poorer place chemically. A star that quietly vanished into a black hole with little ejection would not contribute in the same way. So the very existence of a neutron star phase for some collapsing cores helps determine which stellar deaths become richly ejective and which do not. This does not mean that every supernova outcome rests on one single switch, nor that black hole formation always prevents all meaningful ejection. Reality is usually more complicated and less eager to cooperate with slogans than one might hope. But it is fair to say that the distinction between a collapsing core that forms and sustains a neutron-rich remnant for some span of time and one that plunges more directly into black hole formation has significant consequences for what gets expelled into space. The neutron star window is therefore tied to how effectively stellar death becomes galactic enrichment. And galactic enrichment is one of the most important background processes in the universe. The early cosmos, after the first few minutes, was rich mainly in hydrogen and helium, with only traces of slightly heavier material. That was enough to make stars, which is convenient because without stars the later story becomes awkwardly short. But stars then had to build almost everything else. Through fusion they made carbon, oxygen, silicon, and many other elements up through the iron group. Through explosive events and neutron-rich environments, still heavier nuclei could form. The periodic table as it matters to planets and biology is therefore a historical achievement. It had to be made. The neutron star balance enters this achievement in more than one place. First, as just discussed, it influences which core collapse events successfully explode and eject matter. Second, neutron star mergers themselves are among the leading sites for producing some of the heaviest elements in nature. When two neutron stars spiral together and collide, the event is not merely a spectacular gravitational wave source. It is also a site where neutron-rich material can be ejected and processed into heavy nuclei through rapid neutron capture. That awkwardly modest phrase, rapid neutron capture, hides one of the more dramatic alchemical sequences in the universe. In such environments, nuclei can absorb neutrons so quickly that they build up into very heavy, unstable forms and then decay towards stable heavy elements. This is one of the major pathways by which gold, platinum, uranium, and other very heavy elements are thought to be made. Now the relevance of the neutron star window becomes even more obvious. If neutron stars did not exist as stable, compact remnants in that narrow mass range, there would be no neutron star binaries to merge in the way we observe. If almost every sufficiently massive remnant became a black hole immediately, the population of neutron stars would be drastically altered. The frequency, character, and outcomes of mergers would change. The amount of neutron-rich ejecta available for heavy element synthesis would change. The later chemical makeup of galaxies would change. This is one of those lovely and slightly unsettling facts that make physics feel more interconnected than good emotional hygiene might recommend. The existence of gold in a ring, iodine in a thyroid, or uranium in a mineral deposit depends in part on whether nature permits neutron stars to exist before black holes take over. A narrow balance in dense matter physics and relativistic gravity ends up influencing the inventory of elements available to future worlds. The line from neutron stars to wedding rings is not immediate, but it is real. The line from compact object mergers to the chemistry of planets is real too, and once heavy elements are available, the universe acquires new possibilities. Rocky planets require elements heavier than hydrogen and helium in abundance, silicate minerals, iron cores, metallic compounds, surface chemistry, magnetic fields arising from differentiated interiors. All these belong to a universe that has already passed through generations of stars and catastrophic deaths. Gas giants can be made from lighter ingredients, certainly, but Earth-like worlds need a much richer menu. Carbon for organic chemistry, oxygen for water and rock, phosphorus for biology, iron for planetary structure and biological utility, calcium for bones, sulfur for proteins, trace metals for enzymes, and on through the periodic list of consequences. A universe with only primordial elements would be simple in a very bleak way. So when we say this delicate balance helps make planets, we are not speaking figuratively. It is part of the chain by which the raw ingredients of rocky worlds are synthesized and dispersed. Massive stars evolve and die. Some leave neutron stars, some explode in ways shaped by the behavior of neutron-rich cores. Some neutron stars later merge, producing additional heavy elements and ejecting them into space. Interstellar clouds become enriched with the accumulated debris of these earlier generations. New stars form from that enriched gas. Around some of those stars, disks of dust and gas condense into planets. In those disks, heavy elements are no longer rare curiosities. They are building materials. There is an almost agricultural quality to the process, though it would be unwise to stretch the metaphor too far in a universe that handles farming by exploding stars and colliding neutron remnants. Still, the principle is similar enough to be useful. Material has to be processed, returned, mixed, and reused. The first stars do not simply produce the final universe in one pass. There are generations. There is enrichment. There is recycling on scales so large that the word recycling feels both accurate and absurdly understated. Neutron stars and their delicate balance are part of that cosmic reprocessing system. And then, much later, from the point of view of a human lifetime, though still well within the ordinary patience of galaxies, chemistry becomes interesting enough for life. This part of the story should be handled with a certain care because life depends on many things. Stable stars, long-lived planetary environments, liquid solvents, complex chemistry, protection from sterilizing violence at least often enough, and a long list of contingencies not fully understood. It would be silly to reduce all that to one compact object threshold and call the matter settled. But it would be equally silly to ignore the role of elemental abundance. Life as we know it is chemically demanding. It uses not only carbon, hydrogen, nitrogen, oxygen, and phosphorus, but also sulfur, iron, magnesium, calcium, sodium, potassium, chlorine, trace metals, and a great many other ingredients in structural, electrical, catalytic, and metabolic ways. Those ingredients had to come from somewhere. They were not waiting in full richness at the beginning. They were made in stars and in violent astrophysical events. The heavy element budget of a planet is a historical record of prior stellar generations and compact object outcomes. So while one must not say that neutron stars made life in some exclusive heroic sense, one can certainly say that the universe's ability to produce and preserve neutron stars within a narrow window contributed to the chain of enrichment that made life-friendly chemistry possible. There is also a subtler consequence. The balance between neutron stars and black holes affects not just what elements are made, but how much matter remains available outside horizons. This is a point worth dwelling on. A black hole is in many ways a magnificent act of removal. Matter crossing the horizon no longer participates in the outside universe in the same way. A neutron star, by contrast, remains an active astrophysical participant. It can merge, accrete, radiate, eject, and interact. So a universe in which neutron stars occupied a different range, or were dramatically rarer, would not merely have different compact remnants. It would have a different style of matter circulation. That circulation matters for planetary systems because planets form from the leftovers, not from the cores of stars directly. They form from disks of enriched material around later generation stars. The richness of those disks depends on what previous stars contributed to the surrounding medium. A universe that traps more of its processed material quickly behind black hole horizons might still make some heavy elements, of course, but the balance of availability would shift. A universe that allowed neutron stars to survive in greater abundance might distribute those materials differently. The exact cosmic chemistry would change. Even beyond element creation, supernova themselves influence star formation by stirring, compressing, and enriching interstellar clouds. Shockwaves from stellar explosions can trigger collapse in nearby gas. They can sculpt nebulae and redistribute momentum. So the outcomes of massive stellar death shape not just composition but structure. They help determine how the next generation of stars and planets forms. And since neutron star formation is embedded in the physics of core collapse for a significant class of stars, the neutron star window once again acts not merely as an endpoint, but as a participant in the larger ecology of galaxies. One of the pleasing things about this whole chain is that it rescues compact object physics from the accusation of being too remote. It is remote in location, certainly. Most of us do not keep neutron stars in the neighbourhood, and if we did, the property values would suffer in ways beyond ordinary planning law. But in causal influence, neutron stars are woven into the fabric of later ordinary existence. The calcium in a bone, the iron in a planet's core, the gold in electronics, the iodine in tissue, all stand downstream from the universe's ability to process matter through generations of stars and extreme events. The narrow balance that permits neutron stars but not unlimited neutron stars is one of the rules that shaped that processing. There is a further elegance here, because the balance is productive precisely because it is delicate. If neutron matter were easy and stable across a huge range, the whole dramatic sequence of collapse, explosion, remnant diversity, and merger behavior would not look the same. If it were too hard to sustain at all, many stellar deaths would rush more directly into black holes, and the astrophysical landscape would again be different. The richness comes from being in between. The universe is often most creative at thresholds, and this is one of its finest examples. The neutron star is neither an ordinary star nor a black hole. It is an intermediate outcome, and intermediate outcomes are often where complexity lives. That observation applies more generally than one might first expect. Too much stability can be sterile. Too much violence can be sterile too. Complexity often emerges in regions where things are constrained but not extinguished, dynamic but not annihilated. Neutron stars embody that on a spectacular scale. They are born in violence, persist in a narrow compromise, and influence the chemistry of calmer worlds that may arise billions of years later. The same universe that permits a city-sized object with more mass than the Sun also permits seashells, blood cells, and mountain snow. Those are not unrelated facts. They are joined by a long chain of physical history. There is also a quiet answer here to a question people do not always know they are asking when they hear about exotic astrophysics. Why should I care? Why should the death throes of massive stars or the merger of compact remnants matter to anything except specialists with excellent chalk and a tolerant attitude toward impossible numbers? The answer is that these events are part of how the universe became chemically mature. They are part of why the cosmos progressed from simple primordial gas to a place where rocks, atmospheres, oceans, and organisms could exist. To care about neutron stars is, in a roundabout but honest way, to care about the history of matter before it became a world. And perhaps there is something deeply reassuring in the fact that ordinary life depends on extraordinary ancestors. We sometimes speak as though nature were divided into the dramatic and the familiar, the cosmic and the domestic, as though black holes belong to one universe and rivers belong to another, but they do not. The domestic world is made from the ash and aftermath of the dramatic one. A planet is not an escape from astrophysics, it is one of its later chapters. Biology is not a rebellion against stellar history, it is a consequence of it. Every living thing is, in this sense, a beneficiary of ancient thresholds. That brings us back to the delicacy of the balance itself. One can imagine many possible universes in broad conceptual strokes. Some might produce stars but no rich heavy chemistry. Some might make black holes efficiently, but leave little room for long-lived intermediate remnants. Some might alter nuclear binding or particle masses enough to change stellar evolution profoundly. Our universe happens to permit a narrow mass range in which neutron star matter can exist stably. That permission influences supernovae, mergers, and heavy element production. From those come rocky planets and chemically versatile environments. From those, eventually come beings who can ask where the elements in their bodies were made. It is difficult not to feel a certain gratitude towards such a chain, even if gratitude is not usually considered a rigorous scientific category. Not gratitude in the sense that the universe intended any of this, because physics offers no evidence that the cosmos had us in mind while compressing stellar cores past the destruction of atoms. But gratitude in the quieter sense of recognizing that the conditions allowing complex life are built from many narrow physical facts, and this is one of them. The neutron star window is small, stern, and entirely indifferent, yet it is part of why the world later becomes generous. What makes that especially striking is how roundabout the path is. Life does not emerge because the universe directly set out to produce life. It emerges because physical laws allow stars to form, burn, die, explode, collapse, enrich, merge and seed later generations of worlds. Somewhere in that chain, The maximum mass of a neutron star matters. Somewhere in that chain, the refusal of tiny neutron clumps to self-bind matters too. The whole story depends on the existence of a middle ground. Enough gravity to force neutron matter. Not so much gravity that every such remnant vanishes at once into a black hole. A narrow middle, and from that middle, abundance. So when we say this delicate balance makes supernova, elements, planets, and us, the statement is not mystical, it is historical and physical, and the balance helps determine which stars explode in ways that enrich the cosmos. It helps determine whether neutron stars exist to merge and forge heavy elements. It helps determine how much processed matter remains available to future generations of stars and planets. It helps shape the chemistry from which rocky worlds and biological systems are built. It is one rung in the ladder from subatomic law to conscious life, not the only rung but a genuine one. And that leaves us in a rather remarkable place. A question about stacking neutrons has become a question about why the universe is chemically rich enough for complexity. A story about compact remnants has become part of the story of planets and living bodies. The balance between quantum mechanics and gravity, narrow though it is, turns out to be one of the hidden structural features of the cosmos that allows violence to become fertility. That may be the strangest and loveliest result of all. The universe does not merely survive its extremes, it uses them to make later gentleness possible. From here, there is only one step left, and it is the quietest one. Once we have seen that this narrow interval between too small and too much helps make the visible, structured, chemically generous universe we know, the final question is not only how it works, but what it means to live in a cosmos so dependent on such precarious balances. Because the story of neutron stars is not just about collapse, it is also about the fact that reality often gives us worlds not through broad safety, but through narrow survivals. There is something quietly unsettling about realizing how much of the universe depends on things almost failing. We are used to thinking of stability as broad and generous, as though reality were built on deep, comfortable margins. We imagine the world as something that works because the laws are robust, because matter is dependable, because stars shine in orderly ways and planets circle them with the reliable confidence of long practice. And at one level that is true. The universe is dependable enough that patterns hold, that structures endure, that science is possible at all. But when you look closely at certain thresholds, especially the ones we have been tracing tonight, you begin to see that much of this dependability is not spacious. It is narrow. It is negotiated. It exists because the cosmos can hover just long enough between one kind of collapse and another. A neutron star is one of the starkest examples of that. Too little mass and neutron matter never truly arrives as a stable astrophysical object. Too much mass and the neutron star cannot remain what it is. Between those two limits sits a tiny interval by cosmic standards, and in that interval some of the most important outcomes in the story of matter become possible. Supernovae happen in one way rather than another. Heavy elements are forged, scattered, and later gathered into planets. Compact remnants persist instead of vanishing immediately behind horizons. A whole chain of a later complexity depends on a state of matter that is not broad and relaxed, but narrow and precarious. That is a strange thing to know. It means the universe is not simply a place where things exist because they are easy. It is also a place where things exist because they are just barely allowed. A neutron star is not a casual object. It is matter hanging on under crushing conditions, neither too little to form nor too much to survive. And from that hanging on comes consequence after consequence. If one wanted a symbol for how much the cosmos can wring from a slim margin, one could do worse than a neutron star. There is a temptation, when confronted with that sort of narrowness, to feel uneasy. One can understand why. We tend to associate stability with safety and narrow thresholds with danger. If a bridge holds only under very specific load conditions, one feels less inclined to dance on it. If a machine works only when tuned exactly, one worries about what happens when it drifts. So what should one make of a universe in which some of the great structures of later existence depend on balances this delicate? Is that not a bit alarming? Should it not make reality feel flimsy somehow? Perhaps. But perhaps it should also make it feel more interesting. Because the truth is that complexity often does not emerge from unlimited safety. It emerges from tension. It emerges where competing influences are both strong enough to matter, and neither one is permitted to erase the other too quickly. Stars exist because gravity pulls inward, while pressure pushes outward. Planets form because matter in disks neither remains diffuse forever, nor collapses wholesale into one featureless lump. Chemistry becomes rich because atoms are stable enough to endure and reactive enough to combine. Biological systems persist because they sit far from equilibrium, constantly maintaining order in a universe that would otherwise prefer the easier route of disorder. Again and again, the fertile regions are not those where nothing can happen. They are those where too much can happen, but not all at once. In that sense, the neutron star is not an exception to the style of the universe. It is an extreme example of one of its favourite habits. Reality makes lasting structure by balancing on collapse. And that phrase, balancing on collapse, is perhaps not as bleak as it first sounds. Collapse is only one side of the story. The other side is resistance. The universe is full of things that resist in interesting ways. Electrons resist being crowded into identical states. Nuclei resist being torn apart until certain limits are reached. Matter resists compression through quantum rules. Stars resist gravity for millions or billions of years by fusion. Galaxies resist becoming featureless because rotation, cooling, feedback and gravity all interplay. Even life itself is a kind of resistance, a local structured persistence sustained in defiance of easier entropic routes. One should not romanticize struggle too much, because physics does not care for human slogans. But it's fair to notice that the world is full of structures that exist because opposing tendencies meet and hold one another in check. A neutron star simply makes that fact impossible to ignore. There is also something humbling in the realization that what feels ordinary to us depends on thresholds we never notice in daily life. We do not wake each morning thinking about the maximum mass of neutron stars. We brush our teeth, check the weather, wonder where the day has gone before it has properly begun. The ordinary world does not announce its astrophysical ancestry with any urgency. A stone looks like a stone, not like processed stellar debris. Calcium in bone does not arrive with a label reading forged in ancient stars and distributed by violent cosmic history. Gold does not explain itself. Iron does not stand up in the blood and deliver a lecture. And yet all these materials are downstream of a universe that had to find ways of making and dispersing them. The calm world is built out of old extremity. That can change the emotional texture of ordinary things, if one lets it. Not in a mystical sense, not because every spoon is secretly a black hole in waiting, which would make the kitchen considerably more stressful, but in the quieter sense that the familiar world is not separate from the violent one. It is made from its leftovers. A planet is what happens when the debris of earlier stars is gathered, sorted, cooled and reorganized into a new kind of order. Biology is what happens when chemistry, itself a beneficiary of stellar history, becomes sufficiently elaborate to sustain self-maintaining patterns. You are, in a very literal way, built from a universe that survived many thresholds before you arrived. That fact does not make us central, of course. The universe did not spend billions of years carefully arranging neutron star mass limits out of a fond desire to produce mammals with email. Physics offers no such flattery. But indifference is not the same as irrelevance. The cosmos may not care, and yet its structure can still make care possible later on. One of the odd beauties of science is that intention is not required for consequence. Stars do not mean to enrich galaxies. Neutron star mergers do not aim to supply future geology. Gravity does not plan. Quantum mechanics does not aspire. And still, from their indifferent consistency, worlds emerge. That, perhaps, is one answer to what it means to live in a universe balanced on collapse. It means living in a universe where stability is often the child of tension rather than the absence of it. It means inhabiting a cosmos that makes room for complexity not by eliminating danger, but by allowing matter to negotiate with it. It means that many of the conditions that later feel hospitable are the cooled and settled descendants of things that once were anything but. There is something almost comforting in that if one approaches it from the right angle. We are often taught, implicitly, to think of fragility as a flaw. Something delicate seems less trustworthy than something brute and obvious. But nature keeps producing delicate arrangements that are not weak so much as specific. An orbit is delicate in the sense that it depends on exact motion, yet planets can circle stars for ages. A crystal is delicate in the sense that it depends on orderly structure, yet it can outlast empires. A living cell is delicate in one way and astonishingly persistent in another. A neutron star is delicate in the sense that it exists only in a narrow interval, yet while it exists, it can endure for extraordinary stretches of time. Narrowness does not always mean transience. Sometimes it means exactness, and exactness has consequences. One could even say that much of the universe's richness depends on exactness more than excess. The proton and neutron do not differ by an enormous amount in mass, yet that difference matters tremendously. The strengths of interactions need not be wildly different to alter the fate of stars. The maximum mass of a neutron star is not a flamboyant giant number. Compared with all possible stellar masses, yet it changes the inventory of remnants across galaxies. Small quantitative facts, if they sit in the right place in the logic of nature, can shape everything downstream. That is both sobering and marvellous. Sobering because it reveals how much follows from details. Marvellous because it means even subtle laws can create elaborate worlds. This is one reason physics can feel more intimate than its scale suggests. On paper, neutron stars are remote. They concern compact remnants, relativistic gravity, dense matter, and equations of state. These are not the ingredients of ordinary conversation unless one has chosen unusually charming company. But the implications come home. They come home in the literal sense, because the materials from which homes are built, and planets are built, and bodies are built, belong to a universe whose larger history includes these thresholds. The extreme and the domestic are not separate realms. They are linked by time. That time scale itself is worth pausing over. Human beings live on scales of years and decades, perhaps a century if lucky and well looked after. Civilizations count in centuries, millennia if one is generous with continuity. Biology counts in millions of years. Planets and stars count in billions. Neutron stars inherit histories that begin with the lives and deaths of massive stars, and their influence may reach forward into later generations of stellar systems. To think about them is to stretch one's sense of consequence across vast intervals. The heavy elements in a body may have been forged before the sun existed. The iron in blood may once have sat inside a star whose death predated Earth by eons. The gold in a circuit may owe something to the merger of compact remnants in a long-vanished corner of the galaxy. The present is thick with inherited physics. If that sounds abstract, it need not remain so. It can be felt quite simply. To live in such a universe is to live among outcomes you didn't witness, and thresholds you didn't know were crossed on your behalf. The floor, the walls, the sea, the air, the chemistry of your tissues, the stability of the sun, the rocky nature of Earth, all these arrive already accomplished. We step into a finished scene and only later discover that it required a long chain of earlier successes and near failures. Science, at its best, is one of the ways we recover that hidden prehistory. And perhaps that is why questions like this one are so satisfying. They begin in curiosity and end in orientation. At first, we asked how many neutrons one could stack before reality breaks. By the end, we find ourselves looking back at the ordinary world with altered eyes. Not because it has changed, but because we now know more about what had to happen for it to be here at all. The familiar has gained a backstory, and the backstory is severe. Still, severity is not the same as hostility. A universe balanced on collapse is not necessarily a universe bent on destruction. It is simply one in which the same laws that permit structure also permit failure, and often the structure exists because failure was postponed or redirected rather than abolished. A star shines because collapse is delayed by fusion. A white dwarf exists because collapse is halted by electron degeneracy. A neutron star exists because collapse is halted again by neutron-rich matter. A black hole forms when there is no further exposed halt available. One could tell the story as a series of defeats, and there would be some truth in that. One could also tell it as a series of temporary victories, and there would be truth there too. What matters is that the temporary victories are enough. Enough for stars to live long lives. Enough for galaxies to be seeded with heavier elements. Enough for planets to condense and cool. Enough for chemistry to become interesting. Enough for life to emerge and ask questions about what came before. The universe does not promise permanence, it offers intervals, and somehow intervals are sufficient for wonders. There is a modest lesson in that, one not limited to astrophysics. We often imagine that for something to matter it must be final, unshakable, immune to loss. But nature gets immense value from things that are conditional and temporary. A star is temporary, a planet is temporary, a species is temporary. Even proton-rich ordinary matter may not be eternal, depending on which grand theory one prefers and how patient one is prepared to be. Yet temporary does not mean trivial. A thing can be finite and still world-making. A neutron star can exist in a narrow interval and still shape the chemical history of galaxies. A life can be brief and still alter everything in its own scale. The cosmos seems oddly comfortable with significance that does not depend on forever. That thought sits rather nicely beside the image of neutron stars. They're not the final answer to gravitational collapse, and yet their existence matters enormously. They occupy a narrow band between impossibility and disappearance, and in doing so they change the universe around them. Perhaps one should not push the analogy too far, because humans are not compact stellar remnants, and it would be unkind to imply otherwise. But there is something resonant in the idea that meaning can arise in narrow windows, in structures that exist only because certain balances hold for a while. It also changes how one thinks about so-called hostile environments. We often divide the universe into places friendly to life and places hostile to life, which is perfectly reasonable if one is deciding where not to vacation. A neutron star is not a hospitable place. A black hole horizon is not ideal for gardening. A supernova is not restful. Yet these hostile places and events are part of the causal ancestry of habitable worlds. The universe's kindness, if one can borrow such a word from an indifferent cosmos, is indirect. It does not hand out gentleness at the beginning. It often creates gentleness later through violence earlier. That is not a comforting strategy in personal terms, but in physical terms it is extraordinarily productive. And so the thought that the universe is balanced on collapse need not leave us with only dread. It can leave us with a kind of respect. Collapse is real. Gravity does not compromise out of sentiment. Stars die, remnants fail, black holes form, entropy increases. None of that is softened by looking away. But neither is it the whole story. Along the way, matter resists. Structures emerge, heavy elements are made, new stars form from old debris, planets gather, chemistry deepens, life appears. Minds evolve that can trace the chain backward and discover with some astonishment that their existence rests in part on balances so fine that one scarcely knows whether to call them fragile or brilliant. Perhaps they are both. There is one more aspect of this worth considering, and it is the question of perspective. For most of human history we had no idea that neutron stars existed. We did not know how stars were powered, how elements were made, or what happened in the collapse of massive stellar cores. The night sky was visible, but its internal logic was hidden. That changed gradually. Piece by piece, through observation and theory, we learned that the calm lights overhead are participants in long histories of formation, fusion, death, and remnant evolution. We learned that the periodic table is cosmic archaeology. We learned that compact objects can serve as clocks, laboratories, and gravitational wave sources. In learning this, we did not change the universe. We changed our place in it. To know that one lives in a universe balanced on collapse is therefore also to know something about the privilege of understanding. Not perfectly, of course. There is still much we do not know. The interior equation of state of neutron stars is not fully settled. The deepest phases of dense matter remain uncertain. The exact pathways of some heavy element production are still under investigation, but enough is known to glimpse the broad architecture, enough to see that the ordinary world is the descendant of exotic thresholds, enough to feel that scientific knowledge is not just accumulation of facts, but recovery of hidden kinship between the remote and the familiar, and that, I think, is where this long journey finally settles. Not in a grand moral, because physics is not in the habit of issuing morals, but in a sharpened sense of belonging to a reality more intricate than it first appears. We live in a universe where stars are temporary arguments against gravity, where matter can be forced into forms that seem almost unreasonable, where neutron stars occupy a slim ledge between too little and too much, and where that ledge helps make the chemical richness of later worlds. We live in a universe where collapse is never far away in the deepest story, and yet neither is emergence. The two are intertwined. The thresholds are real. The balances are narrow. The outcomes are generous. So if there is any final comfort in the question of how many neutrons can be stacked before reality breaks, perhaps it is this. Reality does break in one sense, again and again. Atoms give up, stars collapse, remnants fail, horizons form. But each breaking opens the possibility of a new arrangement, a new consequence, a new layer of structure elsewhere. The universe does not preserve everything, it transforms enough. And in the long chain of those transformations, somewhere between supernovae and neutron stars and the dust of later worlds, it made a place where thought could awaken and wonder how close everything came to being otherwise.